ಕೋವಿಡ್ ಟೆಸ್ಟ್ ಅಲ್ಲಿ ಆ ಹೆಣ್ಣದು ತೊಗೊಂಡು ಹೋದ್ರೆ 3 ದಿವಸ ಬೇಕಂತಾರ. ವೈಫೈ ಇರ್ಬೇಕಲ್ಲ, ವೈಫೈ ಮಾಡಲ್ಲ. ಸರ್ ಬದಲಾಗ್ಬಿಡ್ರಿ. ಬೇರೆ ನೀವು ಆ ಉದ್ದೇಶ ಬಿಟ್ಟು ಮಾಡಿ. ಅಲ್ಲಿ ಕನೆಕ್ಟ್ ಆಯ್ತು. ಮೊಬೈಲಲ್ಲಿ ಐಟಮ್ ಮಾಡ್ತಾರೆ. ಇದೇ ಮಾಡ್ಬೋದು ಸರ್. ಇದೇ ಮಾಡ್ಬೋದು.
Morning.
ಅವ್ರು ಹೇಳಿದ್ಮೇಲೆ ನೀವು
ನಿಮ್ದೈತೆ
ಕನೆಕ್ಟ್ ಇದೆ, ಇಲ್ಲಿ ಕನೆಕ್ಟ್ ಇದೆ.
Good morning, ladies and gentlemen. With the blessings of the seven Saptarishis of Scaly Society and with the immense support of our beloved chairman, Prabhakar Kore sir, I welcome you all to this one-day online international conference on zero-dimensional materials organized by Department of Physics, PC Jabin Science College, Hubballi. Now I request our beloved principal, Dr. L.D. Horkeri sir, to address and welcome the gathering.
Good morning, madam. Good morning. A very good morning to you one and all. Ladies and gentlemen, I welcome you all for this one-day international conference on zero-dimensional materials. Amongst us, we are blessed with the presence of a charismatic personality, Sri Shankaranaji I. Munwali sir, Member Board of Management, KLE Society, Belagavi, former President, prestigious Karnataka Chamber of Commerce and Industry, Hubballi, who will inaugurate this conference shortly. I extend a warm and sincere welcome to Sri Shankaranaji I. Munwali sir to this international conference. We are having three eminent resource persons for this conference. Dr. T. Paludis, postdoctoral fellow, School of Physics, Aristotle University of Thessaloniki, Greece. So on behalf of all the participants, on behalf of our college, I extend a warm and sincere welcome to Dr. T. Paludis. Welcome you, sir. Another resource person, Dr. S.P. Raju, Assistant Professor, Malnadu College of Engineering, Hassan. I welcome you, sir, sincerely. Another resource person, Dr. Devatin Jana, Research Associate, Lee Kong Chen School of Medicine, Singapore. Sir, on behalf of our college, staff, faculty, and all the participants, I extend a warm and sincere welcome to you, sir. Welcome you, sir. I extend a sincere and warm welcome to Dr. P.R. Jirgal, sir, HOD of Physics Department. I welcome sincerely Dr. Jagdish Angadi, Organizing Secretary of this international conference. At the same time, I would like to welcome Dr. Rajesh Nair, IQAC Coordinator of our college and convener of this international conference. I welcome you all to this international conference. Friends, KLE Society is one of the premier educational society started in the year 1916 by 7 dedicated teachers whom we respectfully call them as Saptarshis. Now the society is running 275 plus institutions all around the globe under the able and strong leadership of our Honorable Chairman Sir, Dr. Prabhakar B. Koreji, well supported by Board of Management, Board of Life Members, Executive Body of KLE Society, Belagavi. PC Jabin Science College is an autonomous, prestigious college of North Karnataka run by KLE Society, Belagavi. PC Jabin Science College is popularly called as Cambridge of Karnataka for its excellence in higher education. Now, the Department of Physics is hosting this one-day international conference on zero-dimensional materials. So once again, welcoming you all to this conference. I will close my speech. Thank you. Thanks a lot.
Thank you, sir, for welcoming the gathering. Now I request Sri Shankarana I. Munvalli, sir, Member, Board of Management, KLE Society, Belagavi, to address this inaugural session.
College Hubballi. KLE Society is one of the last to present pleasure to present before you a brief introduction about KLE Society and one of its prestigious college, that is BC Jabin Science College Hubballi. The KLE Society is one of the largest educational organizations in South Asia, established in 1916. The KLE Society, being headed by our Honorable Chairman, Dr. Prabhakar Kore, ex-member of Parliament, spread over 275 plus institutions all over the globe, imparting quality education in all the streams for the past 100 years. The society has one of the largest, rarest distinctions of being conferred with two deemed universities, one in medical education and another in technical education. In 2016, the society celebrated its centenary. Our Honorable Prime Minister Sri Narendra Modi ji graced the occasion. Further, the KLE Society's Species and Science College was established in the year 1957 for imparting basic science education and nurturing the wonders of science. On its march, the college is re-accredited for fourth cycle and awarded A grade with CGPA 3.43 by NAC. Recognizing the quality science education rendered by college, the UGC has awarded autonomous status. During COVID-19 pandemic, the Department of Physics organized one-day online international conference on zero-dimensional materials, which includes study of theoretical, computational, and applications of solid materials. The conference played an important role in discovering new materials based on simple insight of the structure and bonding. The International Conference on Zero-Dimensional Materials aims to disseminate knowledge and encourage academicians, teachers, research scholars, and students to come together under one roof to share, deliver, and discuss conclusive aspects of their works through online platform. This is an excellent opportunity for the delegates around the globe to interact with the world-class scientists. It is anticipated to widen the scope of interdisciplinary research among teachers and research scholars. Hope you will be benefited by participating actively in the conference. I am happy to inaugurate this function, this international conference, and thank you one and all.
Thank you so much, sir. Now I'll hand over the mic to Sri Santosh Ghorpade, sir.
Thank you, madam. Thank you, madam. Now I request our beloved head of the department, Dr. P.R. Jirgal, sir, to introduce the first guest speaker, Dr. T. Palvadis from Greece. Now I hand over to Dr. P.R. Jirgal, sir.
Good morning to all the fellow delegates. It is my proud privilege to introduce one of the resource person of today's international conference, Theodorus Pavlidis. He has completed his PSc in Physics from School of Physics, Faculty of Sciences, Aristotle University of Thessaloniki, Greece, during 2011. He has completed his MSc in Materials Physics and Technology from School of Physics, Faculty of Sciences, Aristotle University of Thessaloniki, Greece, in 2013. He got his PhD in Physics from School of Physics, Faculty of Sciences, Aristotle University of Thessaloniki, that is in 2016, under the supervision of Joseph Kiosklau, that is Associate Professor. His thesis title was Atomic Scale Structural Modeling of Technology Materials via Computational Analysis Methods. He worked as a postdoctoral fellow in Nanomaterials Lab, that is the College of Engineering, Swansea University during 2020. That is, he worked as a research officer in Nanomaterials Lab, College of Engineering, Swansea University during 2018. He worked as a postdoctoral fellow in Siemens program in 2016 and 17. He was a visiting researcher for nanoparticles by design unit, Okinawa Institute of Science and Technology, Japan during 2015. He worked as a member or a secretariat of the organizing committee for many international conferences organized on defects in semiconductors, solid-state physics, and material science at Thessaloniki, Greece. His academic interest is in the science field that specializes in computational material science. His research activity involves the use of ab initio and classical atomistic modeling methods, takes advantage of modern high-performance computers, and aims to the study of structural, thermal, magnetic, and optoelectronic properties of nanostructured materials for state-of-the-art technological applications. To his credit, 11 research papers in peer-reviewed journals like Journal of Physical Chemistry, Nature Communication, Advanced Materials, Thin Solid Films, Computational Material Science, Semiconductor Science and Technology, Journal of Applied Physics, Physics of Condensed Matter Physics, etc. He acted as the referee for the Journal of Physics, Condensed Matter. He has presented in talks and posters in more than 30 international conferences. He has developed more than 9 scientific softwares. He is having a proficiency in Greek, English, and German. He won more than 5 awards and prizes for the video competitions, invited talk, and oral presentation. With this brief introduction, I present before you the world-class eminent researcher, a resource person, Theodorus Pavlidis. I thank the organizers and delegates for giving me an opportunity to introduce eminent scientists. Thank you, one and all.
Hello. I would like to thank you for the introduction, and I would like to thank the conference people for the invitation. It's a very nice opportunity to present my work at this very nice and interesting conference. Let me share my screen so we can start with the presentation. Can you all see my presentation?
Yes, sir. Yes, sir. It is visible, sir.
Thank you. Thank you very much. So,
sir, sorry for 1 second.
I'm sorry.
Now I request all the participants to mute the audio and video, please, for the smooth going of the presentation and the session. I request all the dear participants to mute audio and video for smooth conduct of the international conference. Thank you. Now, sir, please.
Okay. So my talk will be on large-scale ab initio simulations of nanoparticle support systems. It is a work that I did during the past 3 years or so, working at Swansea University with Professor Richard Palmer and collaborating with Professor Joseph Kioseoglu at the Aristotle University of Thessaloniki in Greece. I will start with an introduction. I was informed that many of the attendants of the conference are pre-graduate and postgraduate students, so I thought it was a nice idea to include some slides about what we do when we simulate things in material science. Just a brief talk, as the introductor said about me. I currently live in Thessaloniki, Greece. This is the White Tower and the port of the city, and I am originally from Thessaloniki. After completing my PhD, I traveled to Swansea, United Kingdom. This is a photo on the right of the new university, the Singleton campus of Swansea University, where I had the chance to work with Professor Palmer. Before that, I was a visiting researcher at the Okinawa Institute of Science and Technology, and there I started working on nanoparticle systems. So what we do when we simulate things in material science, this is a chart showing all possible simulation methods in material science, starting from the very small models and very precise methods, ab initio methods, and going up to finite elements methods, continuum methods. As you can see, the two bars are the length scale and the time scale. Depending on what we want to simulate, we choose the proper code and approach, and we make sacrifices in the time scale of the model and also the size of the model. So what do we specialize in atomistic simulations? We specialize in the more precise methods, the smaller model methods, mainly ab initio methods and molecular dynamics methods, classical molecular dynamics methods. Why ab initio simulations? Ab initio simulations are first principle simulations. The most commonly used theory is density functional theory. What it does is it provides an approximate solution to the unsolvable many-body Schrödinger equation. It has many advantages. It is the only method that takes into account quantum effects. It provides full info of a system's properties. It produces superb geometries in most cases and very good energetics, and has been used to predict actually structures in the real world, which were then realized in experiments. The pseudopotentials used are transferable and universal. We don't have, like in molecular dynamics, a specific potential for a specific system. We use the same potentials for all systems. And it has a lower computational cost compared to other ab initio methods, but still a very high computational cost compared to classical methods. The disadvantages are that still there are several interactions that are not included, or they are included with approximations, van der Waals interactions and many other interactions. Then that the exchange functionals are not very accurate. We have some difficulties reproducing some physical quantities like the band gaps, electronic band gaps, which are underestimated by density functional theory. But with the new functionals produced every year and the new approaches, these problems are now countered. Just a bit of theory behind MD and DFT. I'm not going to tire you with too many equations. Essentially, in classical methods, in the right side of your screen, what we do is solve Newton's equations of motion, the classical equations of motion. Usually, the program needs a potential that describes the interactions between the atoms. What we used in my studies, what I used for semiconductors, was the Tersov potential, which has 14 parameters. And what we usually use for metal systems like nanoparticles are the embedded atom method, or the modified embedded atom method, or the Gupta potentials, which have the MEAM potentials have 14 parameters, and depending on the potential, they are there more or less. And DFT is much more complicated. What it does, as I said, is tries to provide an approximate solution of the many-body Schrödinger equation. To do so, it breaks the Hamiltonian in 4 terms. One is the attractive term between atom and nuclei. One is the Coulomb energy. One is the Hartree energy, and one is the exchange correlation energy. And it uses different expressions depending on the functional, depending on if it's LDA, GGA, GGA, PBE to express this exchange correlation energy. What our programs do essentially in molecular dynamics, the program starts by reading the initial positions and velocities. Usually they are in a text file. It proceeds to use the potential to calculate the forces acting between the atoms. It proceeds to calculate the new atomic positions and velocities. It calculates the output quantities. We can request from the program to calculate a number of output quantities, the pressure of the system, the enthalpy, the potential energy, the kinetic energy, the temperature, many different, and also more advanced calculations, the common neighbor analysis, distribution functions, etc. And then it repeats the same process until either a convergence criterion that we set up is reached, or a time limit or a step limit is reached. What the DFT programs do is start by an initial electron density guess. As the name implies, the density functional theory, the density term refers to the electron density, which is the most important quantity in density functional theory. So it starts by doing an initial electron density guess. It calculates an effective potential based on this electron density. It solves the pseudo-Schrödinger equations, the Kohn-Sum equations. It evaluates a new electronic density and the new total energy. It checks if we have a convergence based on the criterion that we set up. If it doesn't have convergence, it repeats the cycle. This is called the self-consistent cycle. And if it reaches convergence, it calculates the output quantities, the energy eigenvalues, the forces, the electron densities, and it moves the atoms and calculates the new atomic positions depending on the force calculated. Almost 80% of the calculation time is spent on this self-consistent cycle, the calculation of effective potential and the convergence checks. A simple graph showing what we lose and what we gain by these methods. Using DFT, we have very high accuracy, but very low speed. And using MD, we have very fast simulations, but we have sacrifices in the accuracy. A couple of things that I did during my PhD and afterwards. I started working in semiconductors, mostly in nitrides, gallium nitrides, indium nitride, and aluminum nitride, and I built models of them, nanostructures like core shell nanowires or nanowires with embedded disks. I have simulated these systems both with molecular dynamics and ab initio methods. I studied ordering effects in nitrides and in both 3,5 nitrides and silicon and tin nitrides. And as I said, when I moved to Okinawa, Japan, I started working on nanoparticles. In the lower right corner, you can see our work there. We studied the nanoportals, palladium nanoportals for hydrogen incorporation into magnesium films. You can find the list of my works in my ResearchGate profile if you are interested. Just a slide about what we use to simulate these systems. Most of the codes that we use are open source codes and that are maintained and developed by large groups all over the world, but some of them are proprietary and we have to pay for access to them. Specifically for molecular dynamics, we use LAMPS, which is an open source code, a very widely used open source code. It offers a ton of possibilities and it uses almost every possible interatomic potential that there is out there. For ab initio modeling, we used AIM Pro, which is a program from the UK that allowed us to build very, very big models, up to 1,000 atom models. And now we use VASP, which is a program aimed in Vienna, Austria. And this is the one that we have to pay for. But it is the industry standard. Most researchers use this one. Other open source options include ab initio, Quantum Espresso, Gaussian, etc. We use several programs to visualize our results. The most usual, the ones that I use most are Vesta and for ab initio simulations, and Ovito for large MD simulations. And for structure predictions in bulk semiconductors, we use the USPEX structure predictor. And of course, we have to use supercomputers because all these models, all the simulations are very computationally demanding. So we get access to these big machines, which are situated all over the world. And we send our models there to relax and produce results. Typically, our ab initio models, our ab initio relaxations will last for several days for a model of some hundreds of atoms. In molecular dynamics, a relaxation, an initial relaxation of a model of some thousands of atoms can be done in some minutes. But then we have the possibility to run long-scale simulations and simulate melting and other interactions that also can last for some days or weeks. So we are talking about very, very demanding simulations. So I will present two main examples of our work that we did in Swansea University. One of them is the study of the melting of gold nanoparticles, and one of them is gold nanoparticles on graphene sheets. So melting may sound like a very usual thing to study, but in reality, we don't actually know how nanoparticles melt. There are several theoretical models for melting point suppression at the nanoscale. We know that nanoparticles melt at a much lower temperature than bulk materials. Well, the first one was Pavlov's theory in the beginning of the century. It was a thermodynamic model based on the triple point equilibrium of a spherical solid and liquid particles of the same material. Then we had the liquid cell model, which was a thermodynamic model assuming a solid core surrounded by a liquid cell of constant thickness in the proximity of the melting temperature. And then we had the newest one in the 70s, the liquid nucleation and growth model, which was based on the nucleation theory and described melting as the nucleation of a liquid cell on the surface of a nanoparticle, which then spread to the core until a critical radius was reached. The liquid nucleation and growth model, the LNG model, predicts a region where we have a coexistence of a solid and a liquid, but we had no experimental observation of this coexistence prior to melting. Some calculations for small nanoparticles, the size from 1 to 2.5 nanometers, show these predictions for the melting temperatures. Bulk gold melts at 1,000 and something, 1,100 Celsius, and you can see that by all models we have a suppression of the melting point. Very small nanoparticles, 1 nanometer sized nanoparticles will melt at 400 and 300 degrees. Essentially, they are melted at room temperature. So our experimental colleagues went on with the observations of the melting of the gold nanoparticles. To do so, they used size-selected gold nanoparticles that were prepared using a magnetron sputtering source with a lateral time of flight mass filter that allowed a very, very good selection of nanoparticle sizes. And these clusters were deposited on 5 nanometer amorphous carbon membranes, which were on heating chips. These heating chips allowed the researchers to increase the temperature and then observe what happened in spherical aberration corrected TEM microscope. On the right image, on the left image, you can see the 309 atom nanoparticles, the small ones. And on the right image, you can see the much bigger ones from 500 atoms to almost 3,000 atoms. Here you can see a video of the nanoparticles melting as the temperature increases. You can see that they start from very good crystalline shapes, but then they gradually become amorphous. And at a certain point, we have these protrusions. They lose the almost spherical shape of the crystalline nanoparticles, and they have these protrusions shown here and here. So the idea was to use these protrusions, these changes in the spherical shape of the nanoparticles as an indication of surface melting. And after taking several photos of these nanoparticles at elevated temperatures, we set them side by side and started looking for these protrusions that were indicative of surface melting. So the surface melting was determined by observing the onset of these shape changes. We excluded shape changes due to rotations of the particle. We had the simulation atlas to do so. The researchers in Birmingham created a simulation atlas of nanoparticles at many different angles. So the rotations were excluded. And when such a shape change was observed, the surface melting temperature for that particle was recorded as the temperature between the last observed image of the original shape and the first shape change. And the criterion for core melting was the complete loss of atomic structure. So going back to the chart with the predictions based on the three models, if we put the points of the experimental observations, we can see that the circles in this chart denote surface melting, and the squares denote core melting. You can see that surface melting was within the area predicted by the liquid nucleation and growth model, but in the 561 atom nanoparticles and the 1000 atom nanoparticles, we have a big area, a big difference between surface melting and core melting. And this core melting, the nanoparticle melting temperature, was way over the melting of the melting point predicted by the liquid nucleation growth model and even the Pavlov's model. So this raises the question as why there is such a difference between the experiment produces higher melting temperatures for both the surface and the core compared to the LNG model. We had some minor differences between the core melting temperatures that were attributed to specific structural characteristics of each nanoparticle. Sometimes the nanoparticles were not perfect. For example, they had twin structures, or they landed with different orientations on the cluster surface. And this is an observation of the liquid cell formation at higher temperatures. On the top row, you can see 561 atom nanoparticle, which at the 800 Celsius frame shows significant shape change. And at the lower row, you can see a 1000 atom nanoparticle, and the yellow arrows denote these amorphous regions, these protrusions at the edge of the nanoparticle. So this is a local FFT analysis that we did to make sure that we had a complete loss of atomic structure for the core melting of the nanoparticle. In the right part, in the left part of the screen, you can see that the additional spots in the FFT analysis showed that we still had, for example, at 600 degrees, a degree of crystallinity in the cell, while in the right part, at 655 Celsius, the FFT analysis showed that although the central part of the nanoparticle was crystalline, the surface areas were not. We had lack of additional FFT spots. Just to make sure and provide a much better evaluation of the metal, the melting temperatures, we created a numerical analysis model where we used software to image-day software to manipulate to the TM images, and we started by placing a concentric linear mask with 36 segments on the centroid of each cluster. We tracked the points along the perimeter of the cluster, and we calculated the curvature according to this expression. And we used the value of 1.3 as an indication of a big shape change, that indicates surface melting. So this numerical analysis, as you can see the results, for example, this is one of the 561 atom nanoparticles, and this is where we have a surface melting at 657 degrees. This is a 1000 atom nanoparticle where we had the melting at 800 degrees. So to conclude the experimental results, we had surface melting observations by observations and surface melting by numerical methods. We more or less got the same results by both methods. This validated the eye observations and measurements of melting temperature. It was, for example, for the 561 atoms, only more or less 16 degrees Celsius. So we were very sure about these surface melting temperatures. Going back to the question, why we have such a big divergence from predicted melting temperatures, surface and core melting temperatures, we thought that this may be because of the effect of the support that may delay the melting of the nanoparticles. So we moved into modeling to check what happens there. We used these ab initio models, ab initio molecular dynamics of 561 atom nanoparticles. We did several fixed temperature runs from 300 to 1200 Kelvin using 2 femtosecond step for a total duration of 2.4 picoseconds. And then we used an algorithm, a common neighbor analysis, which shows atoms in a nanoparticle that are in phase center cubic crystalline arrangement, in a body center cubic crystalline arrangement, in hexagonal, or they are completely amorphous. So this is a video showing the free nanoparticles melting at several temperatures. These are cross sections of the nanoparticles. You can see these at for different temperatures, and the green atoms are atoms that are recognized by the algorithm as crystalline atoms, while the gray atoms are atoms that are recognized as amorphous atoms. These are the free nanoparticles where no atoms were bound. And the lower row is the frozen facet nanoparticles where the lower facet was fixed in place. The atoms were fixed in place, and you can see that these are completely flat. They were fixed in place to simulate the effect of the support. These are the red atoms in this slide. So we observed that the core of the crystalline core of the nanoparticles was almost twice the size of the core of the free nanoparticles. For example, in 900 degrees, we had 43 atoms in FCC in a free nanoparticle, while we had 85 atoms in FCC in the frozen facet nanoparticle. What was also interesting was that the core moved towards the crystalline facet, the fixed atom facet. So we observed the coexistence of a solid crystalline core and a melted amorphous surface in agreement with the liquid nucleation and growth model. So these are the results that we got. The horizontal axis is the temperature and the vertical axis is the number of crystalline atoms. The pink one is the frozen facet nanoparticles, and the purple one are the free nanoparticles. We used the criterion for surface melting that we had lower than 147 crystalline atoms, which meant that the two outer layers were melted, and the criterion for core melting that we had lower than 13 crystalline atoms, which is the smallest the smallest possible crystalline nanoparticle. And we got these temperatures for surface melting and core melting. We had a difference of 70 degrees for surface melting and of 140 degrees for core melting. This difference was introduced by the frozen facet, which was again simulating the effect of the support. We predict a coexistence region of 400 or 500 degrees depending on the model. The problem with the initial test was that the common error analysis algorithm was that it always recognized one outer layer as amorphous. So we expanded the algorithm. We used a different algorithm to improve on these results. You can see the new curves are the results from the new algorithm. And we improved the prediction for the surface melting at 500 degrees and 586 for frozen facet nanoparticles, a difference between them of 86 degrees. And the coexistence region was raised to 300 degrees for the free nanoparticle and 365 for the frozen facet nanoparticle. So concluding the results for the 561 atom nanoparticles, the by eye observation of surface melting was 619. The numerical method was in good agreement with this. We had a lower surface melting by the simulations, but these were attributed to the pseudo-potential used. Again, as I said in my introduction, we always have some divergence between what we get in the programs and what we observe in reality. But we had a very good agreement for the coexistence region, which was 260 degrees in the experimental studies and a bit more 300 degrees in the simulations for the frozen facet. We expect the experimentally observed solid liquid coexistence region to be between the 300 and 365 because our method, the frozen facet method, is an exaggeration of the interaction of the support, but we proved that it can delay the melting of the nanoparticles by up to 100, 200 degrees. So conclusions for this work: the melting behavior of the nanoclusters was studied using novel methods, both for the experimental and theoretical parts. Single particle melting in the experimental part, single particle melting was observed in real space, and the coexistence of a solid core and a liquid cell was identified. This mechanism was broadly consistent with the LNG model and the good agreement for the solid liquid coexistence region, but it produced notably higher surface and core melting temperatures. And using large-scale ab initio simulations, we illuminated the influence of the support that in simulations that mimic the effect of cluster adsorption. We had a quantitative and qualitative agreement between theoretical results and experimental results. We observed the solid core that was enlarged twice the size in the free nanoparticles compared to the frozen facet nanoparticles, the landed nanoparticles. And we concluded that the main origin of deviations of the experimental work from previous models, which all considered free nanoparticles in vacuum, lied indeed in the effect of the interactions with the support. Therefore, we say that in every study from now on, the researchers have to take into account the effect of the support when studying the melting behavior of nanoparticles. Moving on to the second part of the talk. So in this second job, we studied the binding of large gold nanoparticles on graphene sheets. The motivation behind this work was that these graphene nanoparticle hybrid materials, they constitute binary nanostructures. They have a multitude of applications. They can be used as catalysts, supercapacitors, sensors, biosensors, and they can also be used for energy storage and conversion. They have been used in all of these examples, and the aim was to investigate the effect that surface modifications on graphene will have on the binding of nanoparticles and of their energetical ordering. Gold on graphene doesn't bind very strongly, so we wanted to find ways to improve this binding. And this is an example of a work that how theoretical works can be used in material science. They can be used to save time in the lab. We use this work to predict how surface modifications will alter the binding of these nanoparticles and therefore save time of our experimental colleagues in the lab. We investigated two distinct cases. We had 561 atom nanoparticles with their 111 crystalline facets on the graphene surface. And also we had these gold nanoparticles pinned with their vertices on graphene. And we studied these binding energies with and without a graphene vacancy under the nanoparticle. In total, our models consisted of more than 1,100 atoms, which is a huge model for ab initio for DFT calculations. And since we knew that the van der Waals methods played a role, we tried to take them into account. So this is the ideal interface between the 111 surface of a nanoparticle. The 111 facets of these nanoparticles are trigonal in shape. And this is how it will land ideally on graphene. We have a very small strain, 3% strain on the gold nanoparticle, which can be easily absorbed by the nanoparticle. And the distance between the two is 3.3 angstroms. The nanoparticle is higher, 3.3 angstroms higher than the graphene plane. Again, gold on graphene doesn't bind very strongly. Oh, so these are the three possible nanoparticles for these magic number nanoparticles, the 561 atom nanoparticles. We have three possible structures. We have the cuboctahedral or crystalline nanoparticles. We have the decahedral nanoparticles, and we have the icosahedral, which are the more spherical ones. These are top-down views of these nanoparticles on the graphene sheet. And after the relaxations, the ab initio relaxations, we calculated the total energy, from which we subtracted the energy of the bare particle, the particle on itself, and of the graphene plane. And this way we calculate the binding energy, which was almost 6 electron volts, 5.8 for the cuboctahedral nanoparticle, and almost 7 for the icosahedral nanoparticle, which bound much stronger to the graphene plane. So now we try to introduce a vacancy under the nanoparticle. In graphene, vacancies do not remain symmetrical. When we take a carbon atom from the graphene plane, we have this Young-Teller distortion. These two graphene atoms come closer to each other and they form a bond. and this atom moves a bit towards the down part of the image, and this the symmetric vacancies show a formation energy of 8 electron volts, while the Young-Teller distorted vacancies show a formation energy much smaller one of 7.7 electron volts. And because of this distortion, we have magnetism arising. We have 0.06 magnetic moment of of the two bonded atoms and 0.5 on the lone atom. So we tried placing the vacancy at 3 different places under the trigonal facet of the nanoparticle, one on the edge of this trigonal facet, one at the center and one at the vertex. We found that generally the vacancies prefer being under the center of the nanoparticles. And we calculated the new binding energy, and we found that the binding energy always improved when we added the vacancy by 0.2 electron volts. So by introducing these defects, we made the nanoparticles bind stronger on the graphene. But what happens when the nanoparticles land on graphene with their vertices? Again, these are top-down views of these 3 nanoparticles, the cuboctahedral, the decahedral, and the icosahedral one. You can see the pentagonal shape of characteristic of this decahedral nanoparticle and of the icosahedral nanoparticle. This, if you remember in the first part of my talk, I mentioned that the experimentalists have atlases of images of nanoparticles. These are the images that they have. They look like this, and they use these as a guide to see, to compare with their experimental images and determine if a nanoparticle is a cuboctahedral one, a decahedral one, or an icosahedral one. It is a job that they are trying to develop programs to identify these structures automatically, but as far as I know, they are still doing it by eye. The human eye is much better at identifying structures. So back to the simulation. This is a side view of the cuboctahedral nanoparticle. You can see that the nanoparticle is with a vertex pinned with a vertex on graphene. So we started this part by checking where the carbon, the gold atom wants to sit on top of the graphene plane. One option was on top of a carbon atom. One option was in the middle of a carbon atom hexagon. And we found that it prefers sitting on top of a carbon atom. When it was in a hexagon, the energy was much higher, 0.33 electron volts. And the binding energies, we moved on with calculating the binding energies, which were 2 or 2.5 electron volts, which, if you remember the 5.5 or 7 point something binding energies calculated before, these are much smaller. So now we have the main part of the work, how to fix these nanoparticles with their vertices on a graphene vacancy, which we expected would improve the binding by a lot. This is my favorite movie from Apollo 13. We had to make these nanoparticles fit in these holes. So this is a zoom in on the vertex of the decahedral and icosahedral nanoparticle tips. They are of a pentagonal shape in these 2 nanoparticles, and they are a rectangle in the cuboctahedral nanoparticle. And we tried 2 different orientation, one with the point pointed towards south, one towards north, and 2 different orientations for the rectangles with their long edge along the horizontal plane and one along the vertical plane. And we did all the relaxations twice for each nanoparticle to find the preferable orientation on graphene, on a graphene vacancy. So we found out that there are no big differences between the two orientations. It was almost the same, some milli-electron volts in the decahedral and icosahedral ones, and 0.01 electron volts in the 0.1 electron volts in the cuboctahedral nanoparticle. And importantly, we got binding energies of almost 5 electron volts. I remind you that the binding energies without the vacancy were almost 2.5 to 2.8 electron volts. So we found that the presence of the vacancy under the tip of the nanoparticle improves the binding by a huge 3 electron volts. So this is this can be used as a guide for our experimentalists to create vacancies in graphene before binding the nanoparticles. Importantly, when the nanoparticle is placed on top of the graphene sheet, on top of the graphene vacancy, it restores the Young-Teller distortion. The carbon atoms assume symmetrical shape again, and they are moved a bit outwards. The magnetism that was there because of the different charge distributions now disappears, and the charge is equally distributed between all the these three carbon atoms in the proximity of the vacancy. This is a side view of the nanoparticle. The nanoparticles are much closer to the graphene sheet. I remind you that they were 3.3 angstroms above the graphene sheet when we had the surface on surface. But when we have a vertex on the graphene, it's only 1.6 angstroms. And the carbon atoms in the vacancy are displaced again by 0.1, 0.3 angstroms. Of course, the atoms closer to the vacancy are more displaced, but this displacement disappears after 2 or 3 circles of graphene of carbon atoms. And again, there is almost no strain on the nanoparticle. The nanoparticle is perfectly relaxed on graphene in this specific configuration. These are nice images that we produce. These are called the charge density difference images. This is a possibility that density functional theory and ab initio methods offer us. And this is why including all electrons is important, because we can visualize what exactly happens with the bond and produce these very nice images of the charge density. To produce these images, we do 3 different relaxations. We calculate the electron density of the model with the nanoparticle and the graphene. Then we calculate the electron density of the graphene sheet, and then we calculate the electron density of the nanoparticle on its own, excuse me. And we subtract these 2 charge densities from the charge density of the big model. And what remains is the charge density of the bond between the carbon atoms and the gold atoms. The yellow and blue areas show charge depletion and charge accumulation. So we can see clearly that only one atom participates in the bonding. There is no charge in the atoms above it, which is an important result, since we had 6 to 7 electron volt binding energy when we had the 111 facet on graphene, where we had 20-30 atoms interacting with graphene, and we get almost the same binding energy when we have the vertex on graphene by only one atom interacting with the graphene vacancy. And we had a small charge transfer from the carbon atoms to the tip of the nanoparticle. So to conclude, we found that the vacancy improves the binding energy on the 111 surface on graphene by 0.2 electron volts. the vacancy considerably improved the binding energy for the vertex on graphene case by a huge 3 electron volts, and it brought these binding energies on the same scale as the previous case, the 111 surface on graphene case. The vacancy was reconstructed and to a symmetrical shape, and the nanoparticle was totally unaffected by the bonding. Only one atom participated in the bonding, and no strain was present in the nanoparticle compared to the 3% strain on the surface and a bit more strain upwards on the nanoparticle. We expect this behavior to be more pronounced in smaller nanoparticles where we have less atoms on the surface, and again more pronounced in noble metals with bigger lattice mismatch compared to the 3% between gold and graphene. Other noble metals will probably bind better with the vertexes on graphene, and also we expect D vacancies and 3 vacancies to further improve binding by a lot by forcing more atoms, 5 atoms or 11 atoms in the second and third layers of the nanoparticle to participate in the bonding. But more importantly, what this work showed was the power of simulations and how they can save time from experimental scientists. As we all know, time is money in experimental labs, and the equipment is costly, the reactants are costly. So if we can use computers to save some time from experiments, then we use them in an effective way. So the goal of this job was to serve as a guide for experimentalists to let them know that the deliberate creation of vacancies on graphene sheets will improve the binding of the nanoparticle and lead to stable hybrid nanostructures. So what we aim to do next in this job is investigate how attractive these covert sites between the nanoparticle and graphene are for catalysis, like for nitrophenol reduction and propylene oxidation, where we predict that we will have molecules binding both on the nanoparticle and the graphene sheet. And also investigate in greater depth how the electronic properties of the whole system change with and without the nanoparticle. Again, some of these structures will be used for sensors and electronic devices where we want to preserve the supreme electronic properties of graphene. So to conclude my talk, I want to thank our funders. This work was performed under a Marie Curie co-founder fellowship that I got when I moved to Swansea. The calculations were done at the Aris supercomputer in Greece and the supercomputing Wales supercomputers in the United Kingdom. The first part of the talk is already published in Nature Communications last year, and the second part of the talk is submitted now and is under an evaluation. And if you want more works, again, you can visit my ResearchGate profile. One that might be interesting, done in Okinawa, where I collaborated with Sushant Kumar and Vidyadhar Singh from India. It was the hydrogen flux through size-selected palladium nanoparticles into magnesium nanofilms, and you can find it at this link. Just to show my main collaborators, are Professor Richard Palmer, who is the head of the nanomaterials lab in College of Engineering of Swansea University in the United Kingdom. We have an Instagram page of the group, and again, you can find it on the ResearchGate. The link was too big to include in the slide. And Associate Professor Joseph Kioseoglou in Greece, where I did my PhD, and I have returned now as a postdoc in the physics department. His personal webpage it can be found at this link. So once again, thank you for the invitation to present at this conference, and thank you all for your attention.
Thank you, sir. Sir, thank you, sir. Thank you for your wonderful presentation. Sir, there is one question from chat box. Can you see, sir?
Let me
box.
open the chat because I have to.
Sir, shall I read this question? Shall I read this question?
Okay, let me stop sharing so I can see the chat.
Yes, sir. There is only one question.
That nanoparticles are difficult to assemble.
Yeah, sir. Yeah, sir. Why is that?
What do you mean by assemble? To bring them together or to build the models of the nanoparticles?
Oh, I think they are assembling the nanoparticle. Means why it is so difficult? Why it is so difficult?
It's not actually very difficult. They have this method, the one that we used the experimentalists used to build these nanoparticles, the one that Professor Palmer created back in the previous decade, this gas phase aggregation method. Essentially, they spatter nanoparticles out of a target, and then they use a mass filter to select the sizes. It's not really difficult to build them. The difficult thing is to build them at a very large scale, because there are methods that they can quickly build nanoparticles using wet methods, for example, at a very large scale for catalysts, but they don't have a very good size control and shape control. And then there are methods that, like this gas phase method, they use the same one in Okinawa too. They have some machines all over the world. They have very good control of the shape and size of the nanoparticles, but they cannot produce many nanoparticles that could be used in an industry, for example. So it's not really difficult to build them, but you have to choose what sacrifices you are going to make. Are you going to sacrifice the quantity, or are you going to sacrifice the quality of the nanoparticles?
Yes, sir.
So depending on where you want to use them, you choose the method. And of course, industry is always interested in large-scale methods. So I know that they prefer large-scale methods. So yes, it's not really that hard to build them. There are many different methods. It's only a matter of choosing the right method according to your interests to build them.
Yes, sir. Yes, sir. Thank you so much, sir, for your wonderful presentation. And there's a lot of the good feedback from the YouTube channel as well as from this Zoom chat box, sir. Right, sir. Thank you so much, sir. Thank you so much for presenting your research work, sir. Thank you so much. Now I request Professor Lata Sedinal Madam to introduce the next speaker. Now over to Lata Sedinal Madam. Madam.
Yes. Good afternoon to one and all present here. I, Srimati Lata Shidana, Faculty, Department of Physics, KLE Societies, PC Jabin Science College, Hubballi. Good afternoon to one and all present here. I, Srimati Lata Shidana. Good afternoon to one and all present here. I, Srimati Lata Shidana, Faculty, Department of Physics, KLE Societies, PC Jabin Science College, Hubballi. Once again, welcome you all for one-day online international conference on zero-dimensional materials organized by prestigious KLE Societies, PC Jabin Science College, Hubballi, Karnataka, India. So to begin with second technical session, we are very fortunate to have young and dynamic personality as a resource person who has joined us, Dr. Raju SP, Assistant Professor, Department of Physics, Malnad College of Engineering, Hassan. It gives me immense pleasure to introduce him. Dr. Raju SP, currently working as Assistant Professor, Department of Physics, Malnad College of Engineering, Hassan. He has designated earlier as a Senior Research Fellow, SRF awarded by BRNS in 2017-2018, and also as a Junior Research Fellow, JRF awarded by BRNS in 2015 to 2017, and as Project Assistant Grade 2 awarded by UGC PERS in 2014 to 2015. Sir has completed MSc in Physics in 2012 from Mysore University, Manasa Gangotri. Later on, he pursued his PhD degree from Mangalore University, Mangala Gangotri in 2018. Sir has published 5 papers in peer-reviewed journals, 5 papers under review, and 3 conference proceedings, and also 9 papers in national and international conferences. Sir has received Best Poster Award. He has attended 11 workshops, 2 hands-on training. Sir is life member of Indian Society of Radiation Physics, and also he is editor and author of periodic scientific magazine Vignan. With this brief introduction, I feel glad to welcome resource person Dr. Raju SP. Today, sir is going to speak on the topic Advanced Quantum Science and Quantum Technology. Quantum dots, over to you, sir. Please.
Thank you, madam. Thank you. We'll share the PPT so that I will start. Just a minute. Okay, so is the I think the PPT is visible.
Yes, sir. Yes,
Am
sir.
I audible, sir, clearly?
Yes, you are audible, sir.
Okay. So while choosing the topic, I was in confusion that which topic I have to choose because I worked on nanotechnology and quantum dots. So, but now, so because of the confinement effect is the major focus, everything is, I mean, quantum is getting everywhere around. So that is why I simply replace the word from nanotechnology to quantum technology and nanoscience to quantum science. Okay, so that is what the motto behind using this advanced quantum science and quantum technology. I'm thankful to the organizing committee to giving me an opportunity to present the topic in here. The contents I will be going through in this lecture will be, I mean, the invited talk will be, in the very beginning, I will try to give brief introduction to the nanotechnology, and later I will jump into the nanoparticles and nano regime, and synthesis of techniques and quantum dots, quantum confinement of QDs, QD in the sense quantum dots, optical properties of them, structural and composites of QDs, hydrothermal method, that is what the method I used while doing my research, and even I'm using that. The properties of QDs, the so synthesized quantum dots, irradiation effects on quantum dots, and not only the synthesis, so I mean the synthesis in the sense the core quantum dots, we extrapolate that synthesis method to have the core shell or core multi-shell quantum dots, and even we try to embed these quantum dots on different hybrid, different materials, 2D materials like graphene or some polymers as well. So, and later I will jump into the quantum computers and the differentiation between classical and quantum computers, why they are different, and quantum principles, single qubit operation, quantum algorithms, and quantum computers companies. So that the topic I will be covering in here will be in the first layer of knowledge. So even the research topics also, the analysis and all. However, I have put number of slides in here just for the information. If somebody wants, we can go back and fetch the information, but I will be running through the slides, the technical slides. So nanotechnology, this word doesn't require so much of introduction nowadays. The technology, it is simply, it is a collection of techniques or skills, methods or processes which have been built based on the scientific knowledge. So, but this nano is getting into everything. So this nano is a great adjective for number of units like nanometer, nanoamps, nanovolts. but this nanometer is very catchy. So what is this nano? So nano etymology, if you think about it, so it is simply nanos from the Greek, that is Latin, in the Latin dwarf in the sense it is short. So how to realize that? So if you have 1 meter scale, if you divide that entire 1 meter scale into 10 power 9 parts, equal parts, then each part will measure 1 nanometer. So if we want to calibrate that size with our daily regular objects, then it is better to have the human hair. So that human hair will be approximately measure 20 micrometer. Then if you cut that 20 micrometer 20,000 times, then one part will be the 1 nanometer. Or 3 gold nanoparticles, gold atoms, no, sorry, not nanoparticle, not into the nanoparticles. So 3 gold atoms lining up together to make 1 nanometer. So this is what the timeline of the nanotechnology, how it was evolved. Actually, this is not the actual timeline, because we knew the concept of this nanotechnology unknowingly. We used this nanotechnology earlier, but we did not label it as nanotechnology. We will come to that point. However, consciously, we registered this nanotechnology as nanotechnology after the Richard Feynman talk, that is in the Caltech University in 1959, where while he was discussing, he was very peculiar in explaining things, and he used to predict so many things, predict in the future things. So in that case, I mean, he simply said there is plenty of room at the bottom by referring it to a tip of pin. So which means we can put the entire Britannia encyclopedia crushed down to on that tip of the pin, which means not physically the book. The information which has got can be stored on the tip of the pin. We always think that tip of the pin is highly unstable equilibrium because the area is very short, but he thought that there is a lot of space in here because there were number of atoms available on that platform. Because until there, everybody thought atoms were simply an abstract quantity where we will use it for calculation, but we will not be using them, or we cannot manipulate them effectively. But after this, many scientists or research institutions took this as serious and went on doing research. And at 1990, the IBM physicists, they wrote IBM letter by 35 xenon atoms. So that is what you can see it on the screen. So just a minute. Yes, in here. And government in USA, these are all the milestones of this nanotechnology. In 2000, it initiated the National Nanotechnology Initiative with a lot of fund. And even in our government, India, the government funded in 2007 the nano mission. It started, and worldwide now there is no lab where we cannot think about this nanotechnology. So nanotechnology is getting into everything. So this is a keyword, nano, the same technology, same science, same particle, chips, structure, everything, but the nano is getting into everything. So also everything is getting into nano. So because of this COVID situation, I have seen a sanitizer where on it was written, this is nanoparticle sanitizer. So which means what, we are bringing down the entire technology, whatever the technology we had, and we are trying to look everything in the view of nano. So it is purely based on the dimensional jump. So we knew what is macroscopic particles. We had seen number of particles, I mean celestial body and the objects around us. But after jumping into micro, we could see the viruses, bacteria through microscope. And now we have jumped to the nano. So I do not know what will happen in the future, but this is what the timeline we are jumping dimension one by one. So that is what nanotechnology concept was unknowingly known long ago. This is what the usual picture that we will see in any nanotechnology talk, that is Lycurgus cup, which means what they had used the gold silver nanoparticles colloidally dispersed in a glass so that if you, depending on the direction of the light you're throwing, the color will be different, and even the excitation wavelength. So because in Roman they use this, and we do not know, because so many what examples might have gone unnoticed, but this is what the thing we know, that it might have started at that time. So this is nanoparticle. Nanoparticles are the essence of this nanotechnology. So nano-sized particles are nothing but nanoparticles in a very simple way. So of course the domain will be different, 1 to 100 nanometer or 1 to 50 nanometer. But one thing is very important, that we declare this this material has crossed its nanoparticle regime when it started behaving peculiar. Because in that situation, because of the surface to volume ratio, or the van der Waals force is a weak force, but when the material enters into the nano regime, the van der Waals force might get dominated and the gravity might go uninfluenceable. So there are so many changes we will see when the material enters into this nano regime. So that is what, and functionality of the material might be enhanced by reducing its size, followed by increasing interacting surface area, which means what, if we have a material, so I'll come to that point in here. So here, surface to volume ratio, if you have one unit, that is 1 centimeter, 1 centimeter, 1 centimeter cube, sugar cube or any material cube, the surface area will be 1 into 1 into 1 centimeter cube. So it is very little. So 1 centimeter by 1 centimeter, it is one face area multiplied with 6 faces. So that is how it will be. But if you cut the cube into number of cubes, where each cube is measuring 1 nanometer cube as the volume, then it has revealed so much of surface area, it has been revealed. So that is why surface area is huge now. So it is something like centimeter cube. If you cut it into number of parts, where each part will measure 1 nanometer cube, that is surface area, then roughly it will be the double the size of the football ground. Initially it was simply 1 centimeter, 1 centimeter, 1 centimeter, the dimension in 3 dimension. But now the total area that it will expose or it will offer will be the double the size of football ground. So that is why the functionality of the material will be enhanced dramatically. So that is why there will be lot of changes. Such changes lead to modifications in their properties, like optical properties, electrical property, thermal properties, magnetic properties, mechanical properties, chemical properties, and there are so many properties. And there are specialized and multi-specialized nanoparticles also. So just entering them, allowing them to enter inside their nano regime, in there also there will be some category where we will come to that point, and I'm referring to the quantum confinement effect. And these nanoparticles, special nanoparticles, will be called as quantum dots, which will have the trapped charge carriers or particles in them. So we'll come to that point. Graphene for thermal and electrical, mechanical. So categorization, let us just look into the categorization of nanoparticles. Of course, it is well known, we can classify nanoparticles in number of ways, but based on our nature of discussion, we can classify them. So now I have classified them in the basis of whether they are made out of carbon or metal-based, dendrimers or composites. So this quantum dots that I will be referring, I will be using in my talk, this QD will be from this metal-based. Okay, of course, we can call even sometimes gold as quantum dots, silver as quantum dots, even graphene quantum dots, but I will be referring to these semiconducting metal quantum dots. And synthesis approaches, of course, it is well-known approach, that is top-down and bottom-up. Top-down means you take the chunk and crush it down, so that until you get the powder, where the particle in that powder gets into the nano regime, the nano size. Mostly it is attrition and ball milling and lithography also. The advantages, of course, it is low cost and larger scale, but there are disadvantages as well: surface defects, internal stress, and contaminations. So anyway, these things are known, so that is why I will be running through these slides. Bottom up approach, it is atom by atom, molecule by molecule, cluster by cluster. So often we will call this approach as nanotechnology, because we will be manipulating atoms so that we will be restricting that atom, restricting the size of the material, and we will be functionalizing it. So that is why this approach is very important. And even the colloidal form that I have used in my studies will also be from this bottom up approach. So methods of synthesis, of course, physical method, chemical method, biological methods. So hydrothermal method, if we look at it, then this hydrothermal, it will be confusing sometimes, but it is not chemical completely, it is not physical completely, but dominantly it is physical, because we keep the precursors in pressure with sealed container with raised temperature. The temperature is above, which is above the boiling point of the liquid or solvent that we have chosen. And biological methods also, just a minute. Biological methods also will use microorganisms or bioentities, so that they will eat some precursors and they will excrete, and they will be the nanoparticles. And quantum dots, here I will spend little time. So this particular quantum dot will be semiconducting nano single crystal. So it is a single crystal where each and every atom will be aligned in a particular fashion, and it is nano. The size of the single crystal should be in nano, and this is from the semiconducting material. It might be 3,5 or 4,6 group of the group from the periodic table. So many materials in a single, I will come to this point, many material and single material concept. So there is a quantum dot, that is nanoparticle. Quantum dot is a special case of nanoparticle. So when you allow that light to interact with this quantum dot, it will be absorbed by the quantum dot, and soon after that, the electron and hole pair will be created, and based on the energy that they have got, the separation will happen. Okay, so the separation will happen. They have got higher kinetic energy because they have absorbed some energy, and they are moving apart. But they ran out of material itself, that is size of the material. So that is why they are forcibly confined back into the material. So that is why they will behave peculiar. So that natural length of the exciton will be called as exciton Bohr radius. That it will be for electron also and holes also, and that will be different for different materials. That is the signature of that particular material. If we bring down the physical size of the semiconducting nanoparticle within the natural length of the exciton Bohr radius or exciton as a quasi-particle, then it will start behaving peculiar, and that is how they will show the quantum mechanical effect. So that is nothing but the exciton Bohr radius. Just a minute. So applications of them, applications of quantum dots. Before that, if you look, what are the offerings from these quantum dots? The broad absorption spectrum. So it will absorb huge amount of light or the photons, and short emission spectrum. The FWHM of the emission spectrum will be short. So I'm referring into the direct band gap materials, because they will absorb radiation, that is light, and they will emit light. So it is called as fluorescence based on the lifetime that the excited particle spends in the excited state. And here higher quantum yield, will come to that point. What is this quantum yield? The quantum yield should be higher, and so we will get that higher quantum yield in this quantum dots. Smaller size, so whatever the size you can achieve, because it will be near to 5 nanometer, 6 nanometer. And band gap tuning, so covering almost all useful domain depending on the size. So band gap tuning is the key focus where the quantum dot is put in the limelight. So we can do the band gap tuning or band gap engineering. So that will be covering the useful domain where the visible light will come to that point once again. So exciting multicolored quantum dots using single source. The different size quantum dots will emit different color. So you can put all of them together, and you can use single light source, and you can excite all of them at the same time. Changing their geometry is very easy. That is, if you want to construct core shell or core multi-shell quantum dots with different materials, that can be done. Comparing with dyes, less photo bleaching. Dyes or have got the drawback that they will soon be photo bleached, but quantum dots will withstand with it for a longer time comparatively, and higher stability as well, and higher extinction coefficient, which is related to absorption of light, and quantum yield is high. So this is why and this is where we will use the quantum dots in solar cells. So emission of visible light, absorption of solar spectrum, cell tagging ability, quantum behavior, and even the FRET effect. FRET in the sense Fourier Foster resonance energy transfer spectrum, that is interparticle or intersystem exchange of charge carriers. So solar cells, we will use these nanoparticles in solar cells. It might be, it will be the third generation solar cells that will be called as graduate cell. So that is, instead of using dyes, we'll use the solar cells and will compete with the dyes. And LEDs also, in LEDs also we will use this quantum dots. So that is how the quantum dot LED displays have come. And detectors also, in catalyzers also, and even in quantum computers. So this is hot topic. So when I was in MSc, everybody used to ask me, and even I used to ask myself, that what is the use of learning these quantum mechanics and all. But these quantum computers have found or very useful. I mean, this quantum principle or the quantum mechanics, whatever we studied in MSc or in the degree level, they are very helpful in understanding or moving ahead with this quantum computers technology. And artificial photosynthesis, so using this FRET effect, we can do that. And bioimaging and biotagging, so by changing the functionality of the quantum dots, we can tag it to different cells as well. And they are competitors to dyes, as I was mentioning earlier. So this is third generation solar cells, one by one. The solar cell, of course, these are all the quantum dots, the one which are looking red, and this white one will be or the TiO2 nanoparticles. They are also nanoparticles. These quantum dots will be used as the active medium, where it will absorb radiation, and it will, the electrons will go to the higher energy state, and these hot electrons or hot charge carriers will inject into the TiO2, and these electrons will transport in that direction, and in the opposite direction the hole will be transported. So this is the this is counter electrode, this is the might be ITO. Yes, of course it is ITO, and it will be transparent so that the light will be allowed in this path. So this is the redox reaction will happen. We might use iodide electrolytes, so that it will block the electrons passing in this direction, and it will allow the electrons passing in that direction towards the quantum dots from this counter electrode. So this is what the band structure. So this electron will jump. This is what the half set of this band gap, the band structure of these two material, TiO2 and CDTE. And CDTE will inject electron hot charge carrier back into this TiO2, and TiO2 will transport. So that is how this electrons will travel. And here, so this is sulfur. So they have used sulfur also. So that can be done. So we can use iodine also. And even in QLEDs, quantum light emitting diodes, and in here we will use ITO only, aluminum in the counter electrode, and ITO, this is indium tin oxide, this is transparent conducting layer. This is the quantum dot layer, this is active layer. So from this side, this will always be forward bias, so that is why it will be the cathode, and this will be the anode, and this this will inject electrons from this side, and this will inject holes in this direction, and they will combine within this quantum dot region, quantum dot layer region, to give a light in the ITO direction only, because ITO is transparent, and even this glass substrate is also transparent, so that we can get the light out of it in this process. And application of quantum dots in quantum computers. Of course, I will not be going through this lot of things, but the basic idea is that one electron, if we excite the quantum dot, the electron will go to the higher energy state. So when it is residing in the higher energy state, we'll add another electron into the same state. So according to the Pauli exclusion principle, no two electrons will stay, no same two electrons will stay in the same energy level. So that is why it will pick the opposite direction, opposite spin. So the spin up and spin down will stay there only, while de-exciting the electron, one electron will go away and another electron will come back to the ground state with opposite spin. So that is how we will invert the spin. So we will come to this point once again at the very end of this talk. So we will be exclusively talking about these quantum computers. So biosensing and bioimaging, of course, these quantum dots with different color, we can tag them for different entities for in vivo and in vitro studies. So these are all very useful in this biosensing as well as bioimaging applications. And this is, I was simply going through in the Sigma Aldrich company website, that this will, the quantum dot, core quantum dot cost will be 17,848 rupees per 10 milligram. So this is expensive because this quantum dot is very important material. So if the quality is higher, then it will cost more. And not only that, core multi-shell or core multi-shell quantum dots, they are further cost effective. I mean, they're costly. The quantum confinement effect. This is what the focus, this is what the do all and end all of the entire quantum technology which has been built around it. They're nano-sized, the quantum dots, they are nano-sized single crystals made out of semiconducting materials whose Bohr exciton radius is larger than the size of nanoparticle itself. Okay, so of course we discussed about it. What is Bohr exciton? It's the natural length between electron and hole pair in the material when excited. This depends on effective mass of charge carriers and dielectric constant of the material, which would vary with them. Band gap is decided by the combination of Bohr exciton radius and their physical size of the quantum dots. So therefore, their physical size is in the order or less than the size of the Bohr exciton radius, makes the dot to possess discrete energy levels by decreasing density of states, which varies its effective band gap. So I will be explaining that now. So this is what the thing, why do we call this as dot? Dot in the sense when we put a mark on using a chalk piece or pen on a board or a paper, then we will refer that dot as zero dimension. Even though it has got some area within it, we will consider it as zero dimension, because if you draw a line, then it will be one dimension. Draw a plane, it will be two dimension. But if you put a dot, then it will be zero dimension. So when it is in zero dimension, the charge carriers will be trapped, as we just discussed about it, the exciton Bohr radius, how it will be confined back into the system. So this band gap, we can tune the band gap of the quantum dot, and the band gap will be, the effective band gap will follow this trend. So if it is a bulk material, the energies, density of state versus energy will be continuous. If you increase for 2D materials, it will be a step function, and this is 1D, it will be quantum wires, and 2D it is quantum well, and 1D it is quantum wire, and it will be like this. And for 0D, it will be a single discrete energy level. So this is how it is. If there is a single atom, there will be two energy levels. So let me consider this as the ground state, this as first excited state, and there will be number of other states also, but I will be concerned about these two states for the time being. So it has got two lines, two distinctive single lines, individual lines. But so let us assume that this atom has got one electron, and the sitting chair it has got is one in the ground state, one in the excited state. If you add another atom, then that chair will be doubled. So doubling, of course, will be depending on the degeneracy of the orbital that we are talking about, the energy gap, and the exciton Bohr radius. So this, let us assume that, and that will be different for different nanoparticles also, confinement also, if it is 0D, 1D, 2D, and 3D. But for the time being, let me say that if you add one another atom, then there are two chairs. So this one line splitted into two lines. If you add another atom, then there will be higher in numbers. So if you keep adding number of atoms, then this single line splits into number of lines, and that will make a band like this. So as we can see it in here, this single line was present in here, but because of the widening of the single line, that has become the band, and that is why it has splitted into this. So it has got widening. So that is why the gap has been shrunken. The gap has been squeezed. So if you further increase the number of atoms, then density of states will be higher and higher. So there will be further reduction in the gap, that is band gap. So that is how it will go on. So that is why if you reduce the size of the material, the band gap will be higher and higher. You cannot come back in the reverse way after crossing its bulk band gap. So you can move in this direction. So this is what the equation that we will use for first approximation or second approximation to find out what is the energy levels of quantum dots. Of course, there are number of atoms, so there will be 50 to 100 atoms present in each quantum dot, but still we will consider there is one electron by simply merging all the wave function of electron, and it will be one. So that electron is trapped inside that quantum dot. So we'll forget about the entire material by, of course, there will be number of atoms, then they will offer some periodic force, that is Coulombic force towards it. But if you increase the effective mass of that electron, we can forget about the atoms. So that is how, if the electron wants to pass across from one end to another end of this quantum dot, then there is no atoms, but it is heavy. The electron mass will be heavy. So that is why it will be depending on the mass of the electron as well as hole, and the radius of the exciton Bohr, which means what? The physical length of the quantum dot is also very important. Higher the length, then lower will be the energy gap, because it is in the denominator. So higher in here, higher in the R value, then lower will be lower in the energy gap. So this will be the default, which means what? You cannot reduce the band gap of the quantum dot below this energy gap of this bulk material, as we were discussing. We can increase the band gap, so by doing this. So lowering the size will be shifting the wavelength of the light which is being emitted out of the quantum dot will be called as blue shift, and red shift will be the opposite way around, the other way around. The confinement regions, there are three confinement regions: the strong confinement regions, intermediate confinement regions, weak confinement regions. So strong confinement regions, in the sense, both electron and hole, that is these two are the charge carriers we will consider in the quantum dot, and these two are trapped completely inside that quantum dot, and that will be achieved with the smaller in size of quantum dots, smaller size quantum dots. If you increase the size of the quantum dot, then it will be the intermediate, which means to call it as intermediate quantum confinement, at least one of the charge carriers must be confined to that quantum dot. So if these two charge carriers are out of the confinement, then it is weak confinement, or it may lead to the simply any other nanoparticle, or simply it will attain back its bulk material. It will remember its characteristic of bulk material. So this is the fluorescence property of the quantum dots. When the light has been absorbed by the quantum dot, the electron will go to the higher excited state. But when it comes back to the ground energy state, the color of the light or the wavelength of the light will not remain the same. It is because of the Stokes shift. So some portion of the absorbed energy by the quantum dot will be utilized to heat up the quantum dot. So this is inevitable in most of the cases, and we will call it as phonon, as we will know. and that is nothing but stock shift. And this is not the drawback of this quantum dot. It is very useful for us while using them, and using them in bioimaging or biotagging applications, because if you send light to excite the quantum dots, then the quantum dot is emitting with different color of light, then we can easily distinguish between what is the source of light and what is the emitted light from this quantum dot. This is an advantage also. So blue shift in the sense increase in energy of emission light, shorter wavelength, higher frequency, higher band gap, smaller size of the quantum dots, and red shift is simply the other way around. The quantum yield, this is very important. Oh, sorry, this was the reminder for me that I wanted to put time resolved lifetime spectroscopy spectra also, but I forgot it. Anyway, I'll come to that point. So this relative quantum yield calculation of quantum dots with respect to rhodomine 6G quantum yield in water. So this is my particular study. So what is this quantum yield? Quantum yield is simply the efficiency of absorption and emission of the photons. So if you send 100 photons towards the quantum dot, then it will absorb all of them, or it will, let us assume that it will absorb all of them. But while emitting, it may not emit the 100 photons. There might be 90 or there might be 80. Based on that, we will say it is 90% quantum yield or 80% quantum yield or 70% quantum yield. But while calculating it practically, we can use Peer method also, but I have used this reference method. So this is the quantum yield of the quantum dot that I wanted to calculate the quantum yield. Then this will be the quantum yield of the reference. So we will take any other, we will take the reference like rhodomine 6G dyes, because for dyes the company fellows will give the data, that is efficiency of the quantum yield of that dyes. So that is why we'll compare the quantum yield of that dyes with our quantum dots to say, oh, this is what is our quantum yield. So this is 100 photons the dye is absorbing and 90% it is emitting, and the quantum yield of the dye is this much. Then what will be the quantum yield of the quantum dot if it is absorbing the same amount of light or the same amount of photons and it is emitting this much amount of the photons. So this is quantum yield. This is the intensity, that is PL emission spectra of the reference, and this is the reference. This is our sample PL quantum, the PL emission spectrum, that is area under the curve, and the absorbance of the reference and absorbance of the sample, and this is refractive indices of the reference and the samples respectively. So this is how we'll calculate the quantum yield comparing with and another thing is the time resolved lifetime spectroscopy that we have to use to find out the lifetime of a quantum dot. So we'll use that, and if it is T1, T2, and T3, so which means tau1, tau2, tau3. So we will find out. So based on the process, we'll have the intensity distribution for tau1, tau2, and tau3, and it will be higher for this quantum dots. So what is the advantage of synthesizing quantum dots in quantum yield? Of course, we can deposit this quantum dot on a substrate, and that can be done using lithography or molecular beam epitaxial method, and this that method is costlier but effective, and you can get the perfection which is nearly equal to the ideal cases. But the colloidal method is solution processable, easily dispersible to other matrices because it will be in liquid form, great uniformity, versatility in tagging, ready open for modification all the time, because these quantum dots will be floating inside that liquid freely without touching each other. So this is, we cannot call this as a liquid because this is a colloidal. So there is two phases, one is solid phase and another one is liquid phase within this. So it is not a, that is what the thing, and this is what the different color it will emit. Just a minute, different color it will emit for the same excitation. So this color, it is emitting bluer light, which means the length of the confinement will be lower, which means higher. length of the confinement will be the higher, and the quantum, the physical size is lower, and that is how it will go in this direction. So now core shell quantum dots. Soon after synthesis of the quantum dots, the quantum yield of the quantum dots will not be up to the mark. It might be 30% or 40% because of the dangling bonds or unsaturated bonds around the quantum dots. So because anyway, we will use some capping agents like mercaptopropanic acid or TGA, some other thioglycolic acid, and so many other capping agents, depending on the solvent you are using and depending on the functionality of the quantum dot. Functionality should be possessed by the quantum dot, then you will use different capping agents, and depending on the synthesis method and depending on the synthesis processes, there will be a number of defects created around these quantum dots, because this is bottom up approach. Atom by atom the quantum dot will be evolved. So in that case there will be some residuals, or there will be some dangling bonds created around this quantum dot. So that is why we have to saturate it. Capping agent will help us up to some extent, but we have to look for some other technique so that we will get the quantum dots to have higher quantum yield. So that is what this epitaxial growth of some other materials only, instead of simply using the capping agents. So this is core and shell structure. It will be core, and this is the core. The band gap offset will be this much, and this is type 1, where the core is with lower in the band gap, the shell with higher in band gap. It might be CDT I am using in here, and this is CDS, which is having higher in band gap and lower in the despacing. I will come to that point why I mentioned this despacing in here. And these shells, the shell band gap is higher comparing with the core. And this is type 1. Type 2 is simply opposite. That is, core will be having the band gap offset which is above the level of the high conduction band of this core shell. So that is how so when this quantum dot, the electron has to jump from here to there, it is higher in energy. So that is why the electrons will not do the circus to go to the shell, but it will stay inside this core. So that is how you are confining that electron by avoiding the inter-system transportation, so that it will increase the fluorescence emission of the quantum dots. And type 2 will be opposite, that the valence band will be the conduction band of core and shell. Comparing with these two, shell is more easily accessible. So that is why if you want to take the electron out of that core, then you use this shell to grow around this core of the quantum dot for different cases. So for example, if you want to transport electron from the core, then we have to use this type 2 and type 1, and reverse type 1 and type 2 quantum dots are also available. So, and another thing is not only the core shell or core multi-shell with the same materials or with different materials or with having halides, that is CDT or CDZNTE. So apart from that, we can have composite materials, hybrid materials also, like decorating quantum dots on this graphene. And graphene is well-known material. It doesn't require so much of introduction. It is with higher conductivity because of zero band gap. Zero band gap. So this, if you want to transport electron from one quantum dot to another quantum dot, there will be capping agent around this quantum dot as well as around this quantum dot, which is sitting next to it. So that is why the electron transportation will not be efficient. So if you use such 2D material, that is graphene oxide or graphene, then this quantum dot will give away its electron. When it is excited, it will give away electrons to the graphene, and that graphene will transport electron across. So if you want to use the quantum dots in quantum dot sensitized solar cells, then you simply decorate these quantum dots around this within this graphene, so that if you introduce this graphenes in some places, then electron transportation will be made easy. So I have done some research on this reduced graphene oxide, and I have decorated quantum dots on this graphene oxide. And soon after decorating these quantum dots on the graphene oxide, the emission will be quenched, which means what? The electron, as it absorbs electron, it will go to the excited state, but it will never come back to its ground state. It will go to the graphene. So that is why there will not be any emission of light. So that is why the entire material will look black or dark because of this process. And even we can embed these quantum dots in polymer materials or P3HD or PSS. So as we had seen the glimpse of the LEDs, how does it work? Then we had used this P.PSS as whole transport layers. So in there we can use this quantum dots within this polymer layers, depending on if you want to use it as a whole transport layer or whole blocking layer. So that can be done, or you can use this polymer as a shell around this quantum dot and you can grow it around it. And this is what the synthesis method. I will not be going through this. I will not spend a lot of time in here. It is simply, however, I have used this hydrothermal method, but I have to follow this chemical synthesis methods, that is cadmium, tellurium. So cadmium, tellurium and mercaptopropanic acid. So these three are the precursors in my synthesis case. Cadmium telluride quantum dots surrounded with this MPa, mercaptopropanic acid, and trisodium citrate, it is a buffer layer, and MPa was the capping agent, and CD and TE, these two are the precursor, and I have maintained this ratio, precursor ratio, cadmium telluride, tellurium and MPa. And synthesis chemistry, of course, I will not be going through this, but this is the capping agent. It has got oxygen and OH group. Since there is OH group, it is water soluble. So before attaching to this cadmium, there will be hydrogen atom connected with this sulfur. After attaching, that will be liberated out, and this sulfur will be the interface between this capping agent to the quantum dot, and it will be repeated all around this quantum dot in 3-dimensional. And this is what the method I have used. I prepared the solution medium, pour into this Teflon container and seal it within this stainless steel container and keep it in the hot air oven for 180°. And depending on the requirement of the size I need, I will vary the time of the reaction. It might be 11 minutes, 12 minutes, 30 minutes. And soon after that, we'll allow it to cool down, because we cannot simply open it soon after it has reached 180° and it has elapsed 11 minutes, because we have to cool it, we allow it to cool down naturally to avoid number of defects created around that quantum dot. So that I used to do it for 3 to 4 hours. I used to allow that container to cool down. So after that, we will transfer that to centrifuge tubes, and we'll use the anti-solvents like propanol, some other acetones, depending on the quality you want. Then we'll mix it in the ratio that you want, and we'll centrifuge it with 4,000 to 8,000 or 10,000 RPM for 10 to 15 minutes. Then we will get the quantum dots precipitate. Not it is precipitated, it is because of the centrifugation, the quantum dots will be taken forcibly to the edge of this the tip of this container. So and we will allow that quantum dots which has been stacked at the end of this container, and we will throw the water out or the solvent out, and we will allow it to dry. Okay, we can use the vacuum technique for drying, or I used the natural drying only. I simply put it upside down, keep it upside down for a longer time on the tissue paper. So I used to get the dried quantum dots, and I could make the powders out of it, or I could disperse that quantum dot in different materials. I dispersed it in polyvinyl alcohol, because these two materials are soluble in quantum dot water. So that is why I did that. And also I went on doing that, and I dispersed these quantum dots in PE.PSS also, and we have slides for that also. So the nucleation theory, so earlier this will be the situation: cadmium, tellurium and mercaptopropanic acid, all of them will be present inside this liquid. And when this when the process started, then the local precursor concentration of the precursor is very key parameter to get the quantum dots. We have to maintain the optimal concentration of the quantum dots, the precursors ratio, and at a particular situation the nucleation will start to begin. So that nucleation in the sense the quantum dots will start to make. Quantum dot is in making. So the cadmium, tellurium, these atoms will come together, and around it there will be mercaptopropanic acid, which will be covering this chunk of the cadmium and tellurium what combination of the material. So that is how it will happen. So it has to achieve some critical size. We will call it as critical size, because if we achieve that critical size, then we have finished almost the most of the important portion of the synthesis process. Because if we synthesis quantum dots lower than the size of the critical quantum dots, then it will have Wolfswald ripening will happen. It will dissolve back into the solution only. If you cross the critical size of the quantum dot, then it will make a big quantum dot and it may precipitate because of the heaviness. So gravity may dominate, or there might be agglomeration of the quantum dots, so that will get the precipitation, which will be in black color with no emission. So this is what the situation. This quantum dot which is inside, this is zoomed idealized picture of this quantum dot, a single quantum dot. This single quantum dot is capped with this mercaptopropanic acid, and there is another quantum dot also which is slightly a little bit apart from this quantum dot, and this is the liquid medium. So this is how the quantum dots will be floating inside that liquid, inside that liquid medium. So this is what the spectrum. Soon after that, I have recorded the UV visible spectra. That is, it observed the shoulder peak was appeared around this 530 nanometer, and this is corresponding. So this is how it is. It will go to the higher energy state by absorbing photon, and this is the gap we are referring in here, and that will be 530 nanometer means EG can be h nu h into c by lambda, and h nu h into c. We know that if you substitute what is lambda, then we can get what is this energy gap in electron volt after conversion from joule to electron volt. That is 2.33 electron volt. And this is what the after absorption we can record the emission also, emission, that is photoluminescence, the fluorescence. So sorry, I forgot to mention the difference between fluorescence and phosphorescence. It is depending, we know the concept, of course. It is depending on the time spent by the electron in the higher excited state. If it is less than 10 power minus 8 second, then and it will come back to the ground state with emission of light, then it is fluorescence. And if it crosses that time, if it spends a lot of time in the higher excited state only, with some metastable state present in the higher excited state, then it will be phosphorescence. I will be only concerned with this fluorescence here afterward for this particular topic. That is stock shift. So that have got stock shift in here also. That is 585 and 530 was the absorption wavelength, 585 was the emission wavelength, and the energy gap was reduced because of the phonon emission. That is, energy of the emission of the light was reduced because of the phonon emission. And size and concentration of quantum dots. In the very first level, we will simply take the data of this UV visible spectra and we'll find out what is this extinction coefficient and the concentration of the quantum dots, and this is path length. That is, the if we take the coeds and we'll put it in the quantum dot, we'll pour that quantum dot liquid into that coed, then that will be 1 centimeter width. So that is, well, L will be 1 centimeter, and absorption can be calculated using this. So you can use, if you know what is absorption, of course we can record this absorption using the same spectra. that is spectroscopy, UV visible spectroscopy. So based on that extinction coefficient, we can calculate what is the concentration of the quantum dot. The size of the quantum dot based on this calculation. So this is what the equation, this is a theoretical, this is a model, the practical model where they have considered they have done different studies on this, and they have model devised it. Using this equation, we can calculate, this is what the reference for that, we can calculate the size of the quantum dot. So for this case, it is 2.729 nanometer, and energy gap is 2.33 electron volt, and this is the extinction coefficient. It is huge, and quantum wield was 31%. Of course, it is very low. FWHM, that is half full width, half maxima, is around 30 nanometer because it is a shorter peak. We cannot have the complete curve, so that is why we'll talk about this half full width, half maxima. And this will be the, this is my concentration of the quantum dot that had prepared, 1.753 to 10 power minus 5 mole per liter. So this is X-ray diffraction spectrum, that is we have identified. We took this quantum dot under this X-ray diffractometer, and we recorded these many peaks, and comparing with the bulk material of the CDT of this JCPDF data, we correlated and assigned the peak name as peak number as 111, 220, and 311, and this is what the angle. So I'll be running through this slides now. So here, this will be the capping agent concentration. If you increase the capping agent concentration, then the higher will be the extinction coefficient. Of course, it will be towards the blue shift. Blue shift refers to the lowering the size of the quantum dot, and that is why lowering the size in the sense the availability of higher capping agents, there will be it will lead to the larger number of quantum dots with lower in size. So the theme of this conference will also include the interaction of radiation with zero dimension material. So that is why I have put these slides in here. So when I expose these quantum dots to the gamma radiation, I found out for 0.3 kilogray and 0.6 kilogray and 0.9 kilogray and 1.2 kilogray. For the time being, let us assume that these are all the different doses, and but it will be higher in this direction. As I did that, the color of the quantum dot was completely diminished, and it was looking black. And I thought that it is because of the photo bleaching or photo oxidation, and we went on studying on that. And this is what the spectrum we recorded. However, we felt that it is might be the different pH. The pH is the culprit of this behavior of this quantum dot to reduce or quenching their light emission. And we simply, because if there is a quantum dot in the liquid, the voltage between the quantum dot and the liquid will matter a lot. If that voltage is almost zero, then this liquid will rush into the quantum dot, and it will dissolve the quantum dot back as the precursor. So that is, there will not be any quantum dot. There will not be any quantum dot. So that is why we have to set a medium so that it should favor the shell growth. Actually, we intended to use this gamma irradiation method or irradiation method as a method to grow a shell around this quantum dot. And for different pH value, we did this. So increase in the redshift will indicate larger in the quantum dot size. So here it is redshift in the higher pH value above this pH 7, and below pH 7 it was blue shift. Blue shift in the sense, we'll come to this point in here. So this is emission spectrum. So here also this is pristine, and for pH 6 and 7 it was diminishing or quenching, and pH 10 and 12, here we have got the analysis, complete analysis. This is what the peak intensity and the peak position. So this is the PL intensity. So for the pH 6, it was short-lived curve with soon it became black, and as you increase the pH values, that it used to sustain for a number of doses. And for this pH, particularly for 12, it was stabilized. However, we need to have the increment in the PL spectrum, that is enhancement in the quantum yield. So that is how we understand that the shell is grown. around this quantum dot. But we did this with bare uh, quantum dots without any precursors. We added precursors and we did the same thing, and we found out the increment in the intensity of the quantum dot. So since we are, I will be going short now. So this will be the thing. Just a minute. This will be the thing. As the size of the quantum dot is lower and lower, then agglomeration will happen. So, but maintaining the proper pH will enable that quantum dot to have the suitable situation around it to grow a shell. And we did that by introducing further core shell, I mean the shell material, extra shell materials. So we achieved it, and the size distribution was slightly increased. This is what the thing. And how long do I have now still? Hello. So organizers, how long do I have now still? So I cannot hear anybody. Okay, I will be going further until they respond. So this is the XRD spectrum, and we correlated them, and this is the PL spectrum. And this is what the quantum yield, we achieved up to 70% of the quantum yield by growing shell around the core quantum dot. And this is what the XPS spectrum of the core shell quantum dots. And this is 3/2, 1/2 specifically for this S orbital. And because of the JJ coupling of the nearby atoms, because of the S is passivated around this quantum dot, so there will be slightly change in the chemistry of the quantum dots are in its surface. So that is why there will be shift towards higher band gap. And this cadmium shift was also correlated with the same. And this is how it is. I will be running through. So this is core multi-shell quantum dots. What did we do? We added some extra precursor, and we irradiated it by maintaining some suitable situation, suitable environment, and we grow the core shell, that is CDT, CDS. And after that, we took the quantum dot, we cleaned it, and again we introduced zinc and mercaptopropanic acid as precursor, and we again allow that quantum dot to interact with radiation, and we made the core multi-shell quantum dots. This is what the signature of the same. And this is how it is, because this CDS is with higher band gap. Because of the alignment, the CDS has got lower d spacing comparing with the CDT. So since this CDS shell is very small in thickness, it can elongate the d spacing, or it can widen the d spacing of this CDS. So that is why this higher energy, that is conduction band offset, will slightly forcibly taken below this conduction band of the CDT, and that is how slightly the electron can pass. And this is what the core multi-shell quantum dots, this is the TEM image that we have got. And we have to achieve the epitaxial growth of the quantum dot just to have higher photoluminescence, because if there is lattice strain, one day definitely it will be lattice displace, the edge displacement dislocation will happen, and there will be strain will also introduce some defects. Strain is also nothing but defect, and that defect will quench further the quantum yield. And this is core multi-shell quantum dots. So this is how it is. So this is the lattice strain. If you introduce ZNS, then see if the size thickness of the CDS and ZNS is very small, then it will align forcibly this CDS and ZNS. CDS has got lower d spacing comparing with the CDT, and ZNS, which is further lower comparing with CDS. So it will make epitaxial growth because of the size of the shell were maintained small. So that is how we could manipulate the d spacing without creating any the defects. And this is a survey scan of the core CDT, CDS, ZNS core multi-shell quantum dots. And I will be skipping this now. So this is the sulfur, different materials, different elements XPS spectrum. And we use this biotagging, we use this quantum dot into the biotagging applications also, bioluminescence applications. This is after excitation light, this is before excitation light. This quantum dot, this is a cell, and this cell will be transparent, or when this quantum dot will be glowing, when we attach this quantum dot to this cell, then the cell will also start to glow. So that is how we'll say, oh, this is the quantum dot has the cell is also glowing, and we can track where the cell is moving in vitra or in viva cases. So this is what we applied this quantum dots. We try to embed or we try to tag these quantum dots into this breast cancer cells also. We did that with the help of with the collaboration of Dr. Rajesh Nairi. So one of the he is the convener of this the conference. And we after that we just try to
Hello, sir. Hello, Rajesh, sir. Hello. 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 Call ಮಾಡಿ. Hello. Sir, ಅವರು ಹೋದ್ರು ಸರ್. Exit. Sorry, we are facing some technical issue with respect to the resource person. Please stay. Yes, sir. The audience participants are requested to not leave the session. We are having some technical problem with respect from the resource person end.
So
Yes, sir. Yes, IT. You are. Yes.
Okay, thank you. I will put my slides in the maximizable. Okay, so there was a technical issue in the connectivity of the internet. Sorry. So I will continue with this. So I will be running through these slides so that I can jump into the quantum computers. So this is what. So after this, yes, quantum computers. So the quantum confinement is the actual focus around this zero dimension material or quantum dots. only because of the quantum confinement. So that quantum confinement nature will be different uh, depending on the situation. So this quantum computers, so when we look at the computation of the present day world, so we have laptops and computers, and where there are number of bits. Bits is nothing but bits are referring to the binary digits, and that bit is made out of a capacitor and a transistor. So it is one of it. So capacitor, when the transistor allows the electrons to pass through that transistor, pass into the capacitor. Sorry, there is a disturbance. So pass into the capacitor, then the capacitor will get charged, and that we will refer that state of the capacitor as 1, that bit state as 1. And if it doesn't allow the electrons to enter into that capacitor, then we will call it as 0 state. And manipulation of the 0 and 1, this state 0 1 1 0 0 1, there will be number of bits in that processor as well as the hard disk. So that is how the manipulation of the zeros bits will allow us to have computation that we have today. This quantum computers are slightly or entirely different comparing with the computers that we have today. This is not the extrapolation of the notion of the classical computers. Classical computers, I am referring the classical computers to the computers that we have today on our tables. But these quantum computers, they are still in the laboratory, and these quantum computers is nothing is nothing but the manipulation of qubits. Comparing with the classical computers will manipulate the bits, that is binary digits, and this quantum computers will manipulate the quantum bits. They are called as qubits. So this is the structure of the quantum computer nowadays. So there is nothing like where can we use this quantum computers to have higher high definition, to view the videos with high definition, or can we switch can we play the keyboards, and if you want to do some other things, we cannot do that using these quantum computers. They are very specialized for some particular applications. We'll come to that point. So manipulation of qubits who work under the principle of quantum mechanics is quantum computers, which means earlier a transistor and a capacitor made a bit, that is binary digit, and here you can see the binary digit. This qubit in the sense quantum bit. So this quantum particles, it might be electron, it might be photon, it might be charged ion, atom, it might be charged atom. So these are all the types of the qubits, that is quid qubit, trapped ion qubits, quantum dot qubit, photon qubits, and etc. So this quantum dot will also be used in the case of quantum computation. So we'll come to that point. Of course, this is not completely established field. This field is open for the researchers who can go and do the research on it. But squid and trapped ion and photon qubits are well established. In squid, the IBM is using the squid effect, and trapped ion and photon qubits, there are a number of reputed companies who are using this principle for manipulating for the quantum computation. So quantum states, how do we define this quantum states? So this quantum states will always, we will refer or we will designate with the Ket vectors. So this is bracket, I think it is in the upcoming slides. So let me not, so this is bracket notation. We know that it is famous bracket, Dirac bracket notation. So where we split the bracket into two parts, bra and ket will refer to the states. Okay, and this state will be one of the element of the Hilbert space. So if there are two qubits, qubit 1 and qubit 2, the possible states will be, so for example, if you take the quantum dot, and it can be, there are two qubits, one qubit, which means one quantum dot, it might be in excited state or it might be in ground state. And the qubit 2 will also do the same, excited state or ground state. But if you combine these two, then the excited state, I will refer it as 1, and the ground state, I will the qubit 2, if it is also in the excited state, 1 1. If the first qubit is in excited state and second qubit is in the ground state, it is 1 0. And if Q1, let me simply say this as Q1 and Q2. If Q1 is with ground state and Q2 is in the excited state, it is 0 1. And just a minute. And this both are in the ground state, it is 0 0. So that is how we'll define this quantum dot states for our manipulation of the for our calculations. So sorry, this is not the label, it was simply. So this is what the binary digits that we will use while the computer will use this. So that is 0 1 1 2 3 4 will be conveyed to the computer as 0 1 1 0 1 1 1 0 0 1 0 1. So in here we can say that this 1, this 0 and this 1, this 1 is made out of a transistor and a capacitor where the capacitor is charged, and this 0 is this 0 is referring to a bit which is not charged. The capacitor of this is not yet charged. And in the same way, so let me take the pointer. And in the same way, this one, the capacitor of the transistor capacitor combination has charged. So that is how we will define this as 5. If you want to count what is 3 plus 7, then 3 is nothing but 1 1 and 7 is nothing but 3 1. Or if you want to count this 1 0 0, 3 plus 4, then 3 plus 4 it is 3 1. So that is 3 1, it is 7. So that is how. So 4 plus 3 that we will count. So this ordinary or classical computer will count using this kind of processes. So this is what the time image of our processor, the classical computer processor, where there are number of transistors and combination capacitor combinations. So if you compare the classical computers with the quantum computers, transistors and capacitors are the building blocks. And in here, quantum particles will be the building blocks. It might be, as I was mentioning, the trapped ion or the photon or the quantum dot or the atom itself or the photon and so on. So fast but many steps, so ultimately slower. This classical computers, comparing with the quantum computers, it is faster, but it will take a lot of steps. Will come to that point. So that is ultimately it is slower. So this quantum computers will be slower, but within a single step, it will finish the entire task. So that is ultimately it is faster. Parallel computing is not possible. If you want to have parallel computing, we have to have a number of processors attached with the processor. That is, we have to use multiple processor for parallel computing. That is what the supercomputers are doing. The parallel computing, yes, because of the quantum principles, we'll come to that point. Entropy increases. Landauer's law, that is entropy of the system increases by kT ln 2 times, because in the case of classical computers, we might be using 1 0 0 1. So if we want to operate this AND gate on the 0 and 1, then a 0 and 1 will be the input and the output will be, for example, 0. Then 1 has to be erased. So while erasing, it will heat up the processor. So that is why there should be a continuous fan running over this processor to dissipate the heat. So that is why it is it will simply lose the energy. It will dissipate the energy, but in here remains the same. The entropy will remains the same for an isolated system, because we will create quantum particles by trapping them inside a quantum well. That is, we will try to isolate them from the rest of the world. So that is why they are perfect isolated system. So that is why, according to thermodynamics law, the heat will not be dissipated or communicated with the surroundings. Doubling growth of power when a bit is added using 2n. That is, if you add one bit, then the bit has got two states, 0 and 1, And if you add another one, the another 2 states will be added to this states. So now totally 4. And if you keep adding, the doubling will happen. 4 to 8, 8 to sorry, it is 2n. So if it is 1 bit, it is 2 states. If it is 2, 2 into 2, 4. If it is 3, 3 twos are 6, and it will go on in that way. But in the case of quantum computers, it is exponential growth. It is 2 to the power n. If you add 1 quantum bit, then it will double the power of it. So n is nothing but number of qubits. We'll come to that point now. Sorry, believe me, it is lion only. So this person who is on the other side of this barrier saying, I am safe because we have barriers in between you and me. He is talking to the lion. But lion knows quantum physics, so it can tunnel through this barrier and can eat this person. So failures of Moore's law, why it is mentioned in here? Because we had seen the structure of transistors and capacitor combination on the TEM image in the earlier slides. But if Moore's law states that number of transistors on a semiconducting chip is doubled every couple of years and its cost halved, which means what? Within 1 centimeter by 1 centimeter. For this year, it might be 1 million. Then in the next couple of years, then it will be 2 million transistors that you can accommodate using embedded system on the chip. And the cost will also be halved. And this went on, but to do that, we have to reduce the size of individual transistors as well as capacitors. So if you want to reduce the size of the transistor, then there will be base, gate, and the emitter, and there should be a barrier so that it should allow the electrons to pass through and it should not allow the electrons to pass through. So that barrier should do this job efficiently. But because of the leakage of the electron wave function, this electron wave function, this wave is matter wave. The matter wave is nothing but the probability of finding that particle wave that will be leaked. Some portion of the electron probability of finding that particle wave leaked into the other side of the barrier. So that is why you can see few electrons. So of course, in the case of transistors and capacitor, earlier cases, also we were manipulating the states with few thousands of electrons. So that is why if few electrons are lost, then we did not find any difficulty in defining the states if it is 0 or 1. But in here, since we have reduced the size of the transistor, there are only few number of electrons. There might be 80 electrons, there might be 100 electrons. So that is why these electrons might squiggle through this barrier and present on the other side of the barrier, and this is nothing but quantum tunneling. And because of this effect, you cannot make permanently a resistive path if you want to create a 0 state on the classical bit, because there will be some electrons squiggle through that barrier and it will go to the other side. So that is why it will also show the 1. So that is how we cannot continue using this technology to increase the power of the computation. This is the limitation of this computation, the technology. So that is why everybody thought to utilize, they changed the attitude, they thought to utilize or exploit this drawback as an advantage to change the picture upside down, to construct a computer which will be constructed based on the quantum principles. Okay, so actually Richard Feynman, once he mentioned he wanted a quantum computer, he wanted a computer which can simulate the entire world. So entire world will work on the principle of quantum mechanics. So each and every material around us or object around us will be made out of atoms, and individual atom will be quantum particles. So that is why we have to have a computer which will obey the quantum principle so that we can simulate the entire world, and we'll come to that point. So now if you assign, so how this, what are the tasks can be performed by these classic quantum computers? So if you ask this classical computer, give me the factorial of the number for me, that is 120, then classical computer will feel it is a huge number, because 120 factorial means 120 into 119 into 118 into 117 and so on. It will be a huge number where it cannot accommodate that number. But quantum computer, don't be sad, he is fundamentally like that, because classical computers are fundamentally made not to we cannot do such calculation, a huge calculation using this classical computer, but quantum computer can do this. So this is, of course, we will use majorly two important principles, that is superposition and entanglement. The quantum superposition in the sense, for example, if there is a quantum dot, I'll come to here, what is superposition. So atom is spin up and spin down at the same time. So let me not simply go completely depth into the definition of that. So this is very simple. This atom is having the spin up state, and this is spin down state. So it can have one state at the same time, but according to quantum mechanics, it cannot have. It will be spin up and spin down at the same time. So if atom is excited, it will stay in the excited state, but we did not feel any ambiguity in defining if it is in the higher excited state or lower excited state. But quantum superposition will interfere and it will make this states superposition. So that is why, so 50% of the time it will be, so it is both excited state and ground state at the same time. If there is an electron and there are two positions, L1 and L2 defined positions, and if you find this electron, if you think that electron should present in this L1, no, it will not happen. At the same time, this electron will be present in this L1 and L2 at the same time. So we'll come to that point. And this photon will also be doing the same. It is vertically polarized and horizontally polarized at the same time. So that is why this quantum date, it is not permanently written as 0 and 1. It is both at the same time. It is 0 and 1 at the same time. If you use this as your qubit, this atom is spin up and spin down at the same time, which means you have got 0 and 1 at the same time. So that is how the computation power will be higher. So sorry, I should have put this long ago in this flow of slides. So this is bracket notation. The state of a quantum system is represented using this Dirac bracket, and 0 and 1. So here onwards, we will simply not say that it is 0 and 1 without brackets. So ket vectors will be called as 0 and 1 and will be referred in this fashion only. This is half of the bracket. So we have put the 0 and 1 in here. So superposition of the state will be defined in this way. So this alpha and beta will be the complex numbers, and squaring of them will you will get the probability of finding this state of that quantum system. So this W is the superposition system. So this 0 and 1 at the same time means if there is a coin, if you flip it, when it is in air, it is still flipping, and that state is nothing but superposition, where it is 0 and 1 at the same time. But that superposition will be destroyed when it falls back on the ground, and there might be head or tail skyward. So it will reduce back into the classical states only, but it will be in the superposition state. How do we define that? Because if we do this experiment 100 times, 50 times it will be head and 50 times it is tail. So that is why, so in the superposition state, it will be 50% probability of getting them, head or tail skyward. So that is how this superposition principle will work. And so this superposition principle will increase the power of the computation. So this is how it is. Just a minute, slide is not moving. Okay. So this is what the exponential growth of the number of states, 2 to the power n. So that is exponential with the base 2. So 1 qubit, 2 states, 2 qubits, 2 to the power n, that is 2, 4. So 3 means 2 to the power 3, it is 8. And 4, that is 2 to the power 4, it is 16. So adding of a single bit is doubling the power, doubling the number of states in here. So that is why if you add 300 qubits, then the total number of states that you will get, using them, you can represent the atoms who are present in this entire world. So this is how it is. Once this is the story of inventor of the chess game. So I will simply go through this. I mean, I will not spend a lot of time in here. So there are 64 boxes. Once the inventor of the chess game, he went to the king, and king was he was happy with this work, and he asked the inventor of the game to request anything he wanted, because he wanted to give him a reward. And this inventor of the chess game was logically strong, and he simply said, sir, there are 64 boxes on this chessboard, and by doubling the wheat grains, first box 1 grain, second box 2 grains wheat grains, third box double of that. So if you do that, and at the very end, how much amount of the wheat grains I will get, give me that. So king did not realize the power of this exponential growth, and he simply laughed at him on his own, and he simply, because his duty to offer whatever he wanted because of the invention of such a great game, he employed a person in the palace to calculate how many number of wheat grains that we have to give him at the 64th box. And that person went back and sit, and it took him more than a week to come back to say the number, and that number was this. This has got 19 digits. Even I do not know how to pronounce it, but that will be, if you stack the wheat grain sacks, then that will be such a huge amount of wheat grain sacks, then it will be equal to the height of the Himalayan mountain. If you spread the wheat grains within the Indian territory, then with the 1 meter depth, it will cover the entire Indian territory. So that is what the power of the exponential growth of the states. So that is why this 64 box, that is 64 qubit, can do this. Then what about 300 qubits? So 300 qubits are enough to represent the entire world atom. So this quantum computer, how does it work? So if this rabbit wants to solve this maze and come out of this maze, and this maze is made out of a number of confusing paths, and if you allow this classical computer to help this rabbit, then it will start trialing one by one. It will go in here, okay, it will find a dead end, it will come back, and it will go in, it will travel in the other end, and it will come back. And at one particular step, it might find that particular path, and it will help and take the rabbit out of it. But it is fast. The stepping will be fast. The time duration for individual step will be fast, but it has taken number of steps. But if you ask the same job to be done by the quantum computer, it will find the path, finish the job in its first trial itself. It will not even go for the second trial. Because of the superposition principle, it will spread its path, its trajectory in all the possible ways, and it will find the path in a particular in a first step itself. So that is what the power of the quantum principle, the quantum the superposition principle. The quantum entanglement is another feather to this quantum computer, and because of this is very peculiar, and it will go completely counterintuitive, because so there are two quantum dots. Sorry, it should be upside down. So if there are two quantum particles and they are separated, and they have kept on the either end of the entire world. So this is one end of the world, and the other one is other end of the world. Then if you flip, or if you operate some operation on one quantum system, immediately the other system state will be changed. This is proven practically. And as if the time taken between these two transportation of the information is zero, as if there is no space exists in between these two. So this is what the quantum entanglement beauty. So it is very helpful for this quantum computing. So for example, there, if you flip a coin, it will fall back and it will show a state. It might be head skyward or tail skyward. But if we take two coins and if you flip it, and there is no connection between this coin one is facing head and the coin two is facing tail. There is no connection in between. If it heads, it might the second one might also take the head skyward. But this will not happen in the case of quantum bits. If you consider these two as coins, then if it face head, then it will definitely face down. Okay, that is tail. So this is nothing but this is not simply 50%. This is 100%. If you know one state, definitely 100%ly this state will be that is spinning down or the tail. So this is what the beauty of this quantum entanglement. So if you want to manipulate a single qubit quantum gate, the XNOT gate or Hadamard gate means it is a superposition state. So which means what this is zero state, this is one state, for example, or this is one state or zero, this is zero state. So it is in zero state. So let us assume that it is in zero state, which means what it will show it is in the zero state only. But if you using this some principle, some operation, you can rotate this and you can make it as one state like this. But if you put this state in between this 0 and 1, then it will be facing in this direction. So it is neither 0 nor 1. So this is nothing but intermediate state or superposition state. Now, if you measure what is the state of this qubit after putting this state in this superposition, then 50% time it will show 1 and 50% time it is 0. So it is simply the Schrodinger cat's example analogy. So if you put that cat inside that box and if you go out of the house and inside that box you if you keep something so that the cat will be died, so that it will be 50%. And if you come and open that box, until you come and open the box, you cannot know if it is dead or alive. So in the same way, it will also be in the superposition, but after measuring, it will collapse into one of these two states. So this Pauli gates, that is sigma x, sigma y, sigma z, that operations can be done on this single qubit operation, single qubit. So this is nothing but Bloch-Spear. And I'm simply going through this because next talk will be completely on the advanced quantum computing. So that is why I'm not spending a lot of time in here, and even we are running out of time for this session, I think. This is the timeline of the algorithms for computation built. So initially the Turing machine, and after probabilistic Turing machine, Church Turing thesis, Dist algorithm, Shor's algorithm, and Graver's algorithms. Now it is continuing, and quantum computers hardware is built, but nobody knows how to use it properly, effectively. So few calculations are being done, and there are some guessings that it can be used in AI, it can be used in some other artificial intelligence or deep studies, but effectively that has not been done. But there are preliminary works that have been done, and it is still going on. So we need a proper algorithm to use that or utilize that hardware system. So this algorithms, this Dust, actually he wanted to build a different algorithm. He wanted to build a different algorithm, but everything was the same. That is why he looked into the quantum physics. So he found out that quantum physics can also be used, and if you build the algorithm with keeping in mind the qubit operations, then that will be the better algorithm for these quantum computers, and that will increase the power of the quantum computers. And now it is hybrid computers. This quantum computer, of course, it is being operated, but it is not completely alone operated. We need classical computer support. That is, if you want the 0 and 1 at the same time, but if you measure it, it will collapse back into 0 or 1, but you have to read it. So that is where you will use the classical computer to store that data. So that is why now it is hybrid computer, and it is cloud computer also. It is open for each and everybody. Anybody can access this quantum computer. So IBM, Google, Intel, there are so many reputed companies who have offered or opened these quantum computers to everybody because they have built it, but they do not know how we can utilize this effectively. So that is why they are taking help from each and everybody. So now the coding is also happening, and the coding, this has been built on the Python programming. This is IBM Quizquid, particularly I'm talking about. Of course, we don't have to have the background of this Python programming because everything is graphically interfaced. So this XNOR gate, this is XNOR gate, and if it is H, then it is header mode gate, and this is measurements, measuring devices, and this is Q1, Q2, Q3, and these are all the classical bits. And this is how, if you want to have a qubit, then you can simply add it. If you want to put a operator or a gate in here, then you can simply drag and drop in here. That will work. So that is why it is very helpful if somebody wants to continue in this quantum mechanics or quantum computer. I prefer to, if you want to understand quantum mechanics properly, then it's better to understand quantum computers, because the operation will be very practical, and many of us will not be knowing the practical usage of this quantum computers, quantum mechanics. But when we use these quantum computers and how they are working, of course we will get the glimpse out of these, how we can do this, how we can use these quantum computers, quantum mechanics in future. So these are the companies: IBM Q, Alibaba, Google, D-Waves, Microsoft, Intel, Rigetti, Quantum Circuits, Ionic Q. So these are all the companies who are manufacturing quantum computers. Very sorry. And thank you. That is the end of this, what I wanted to explain. So thank you for the opportunity. So over to you, sir.
Thank you, sir. Thank you for your wonderful presentation, sir. And I think all the participants have taken the advantage of this the session. And there is one question from the chat box, sir. Can you see this?
Just a minute, sir. I'll stop sharing so that.
I think Anshul Rana is asking why the size of the architecture, that is, our motherboard, cannot go below 7 nanometer. If so,
where is it? Okay. So because 7 nanometer means we are having number of atoms which is very less, and individual atom that might be giving 1 electron each. So there will be only few number of electrons where we can, with which we have to play. So that is, if you want to build a transistor with 7 nanometer or below 7 nanometer, then the transistor has to make a permanent resistive path, or it has to open that resistive path for gate action. But if you put that, then what will happen? There will be only few number of electrons present. It might be at the source, and these electrons, because of the lower density of states, combiningly they are almost acquiring the properties of the quantum mechanics, quantum systems. So that is why few electrons may squiggle through this barrier and they may present on the other end. So that is why you cannot say now it is 0, or you cannot say now it is 1, because of these electrons traveling all the way, completely all the time. So they are passing through this barrier. So that is why you cannot permanently make 0 or permanently make 1. So that is the restriction of this.
Yes, sir. Thank you, sir. Thank you so much.
Thank you.
I'm very thankful for your wonderful presentation, sir, from the organizing committee, and
Thank
for
you.
your wonderful presentation. And I announce that there is no any lunch break now. Now we are moving towards the next session. And for that, I request Professor S.V. Angadi, sir, to introduce the next speaker, Dr. Devar Pashtam Jane from Singapore. Over to S.V. Angadi, sir. Now. Yes, sir. Yes, sir. Angadi, sir.
Yes.
Yes, sir.
Good afternoon. Respected Chief Guest, Honorable Member of the Board of Management, Sri S.I. Munwale, sir, esteemed resource persons, beloved principal, sir, dear delegates from across the globe, my learned colleagues and dear friends. At the outset, it gives me an immense pleasure to give the brief introduction of the invited speaker, Dr. Deba Pratim Jana, Research Associate, Lee Kong Chain School of Medicine, Mekano Group, Nanyang Technological University, Singapore, for the online international conference entitled Zero Dimensional Materials, being organized by Department of Physics, KL Society's PC Jabin Science College, Hubballi now. Sir has completed his master degree in Master of Mathematical and Theoretical Physics from St. Anne's College, Oxford University, with a distinction in the year 2019. He involved in research activities since 2017. He represented Oxford University at summer research program to tackle projects ranging from Lie group methods in continuous media, instabilities in hydrodynamics, to simulation of spin dynamics organized by the Department of Theoretical Physics, Perm State University, Russia, as a summer intern between June to August 2017. He became summer intern from July to September 2018 and investigated theoretical models for universal quantum computation and tweaked models to simulate complete set of quantum logic gates of theoretical physics, Leeds University, UK. He serves as a part-time researcher at Data-Driven Enviro Labs from September to January 20 and developed a natural language processing tool to analyze climate action texts submitted by various European cities to identify good and bad actors, and developed statistical packages in R-Topper, forming topic modeling, policy diffusion using temporal network auto-correlation models. He was the visiting scholar at the Center for Quantum Technologies, Arthur Ecarta Group, Singapore, from August 2019 to January 2020. He developed unconditionally secure cryptographic protocols, used classical and quantum information theory to analytically prove security, and ran numerical simulations of security and testing use for quantum satellite communication. At present, Sir is serving as a research associate at Lee Kong Chen School of Medicine, Mekano Group, Nanyang Technological University, Singapore. He is working on developing spiking neural network models to simulate task modeling in rodent formulate computational neuroscience direction of group and integrate with experiments, merging biologically feasible models with traditional reinforcement learning models from zero-shot learning. He invited as a resource person at various conferences. Among them, he was the resource person at international webinar organized in June 2020 at St. Aloysius Autonomous College, Mangalore, India. He was also invited as a resource person for an international conference at Information Security in the Quantum Era, Okinawa Institute of Science and Technology, Japan, during March 2020. However, due to COVID-19 pandemic, it was postponed. In February 2020, he got a license and certificates from Stanford University for his work on neural networks and deep learning. Also, introduction to psychology from the University of Toronto. Accomplishments and awards. He is the recipient of many awards. Few I would like to mention here. In December 2019, he received an Innovative Approach Award for his collaborative work with LA Collaborathon. Aspects Award for Academic Excellence from South Point High School in February 2015. He received many scholarships, among those Saint Anne's Vocational Laboratory Scholarship from Saint Anne College, June 2018. British Petroleum Scholarships from Oxford University in June 2017. Harold Para Scholarships from Saint Anne College in October 2016. And each semester collection prize from Oxford University between 2015 to 19 for the academic merit-based prize based on exams. It will be awarded to 10%, below 10% students of University of Oxford. He is waiting for a patent from for the model, an approved low-cost multi-layered phytospigment solar cell, which was published and expected result by December 2020. And it's proud to announce he worked, he collaborated with the Government of India for this project. In May 2014, he won a gold medal for one out of 13 nationally selected projects at IRIS to represent India at IESEF. In May 2014, he received first grand award for from Patent and Trademark Office Society for the project at Intel ISEF. In 2012, won the gold medal in All India Math Science exam for excelling at National Creative Problem Solving Test. National ranking was 24. With this brief introduction, I would like to welcome the speaker once again to this August online gathering on my behalf and behalf of management, principal staff, students, and delegates. And I would like to express my sincere thanks to the organizer for giving me this opportunity to introduce such an excellent personality. With this brief introduction, I conclude to this introduction program. Thank you very much, sir.
Yes, sir.
Yeah, I guess I will share my screen now. Is it visible?
Yes, sir. It's visible.
Okay. Yeah, firstly, thank you for the very warm and kind introduction. And I would like to express my gratitude for being given the opportunity to present at this international conference on zero-dimensional materials organized by Mangalore University. So the title of my talk is Anions, the Future of Quantum Computing. And this was work that I did partly at Leeds University and partly at Oxford University as part of my master's thesis. So without further ado, I want to begin. So this is the outline of my talk. So firstly, I'm going to motivate the fact that quantum computing is brittle. Then I'm going to introduce anions. Then I'm going to introduce what's called topological quantum computation with anions. Furthermore, I'm going to talk about a very famous example of a topological model, anion theory, called the toric code. And I'm going to introduce how the toric code can support quantum error correction. Then I'm going to talk about Fibonacci anions and how a Fibonacci anion model can support universal quantum computation. And finally, before concluding, I would like to talk about boson condensation in these anion theories, in these topological QFTs. And that is some work in progress. So quantum computing is brittle. So I think the talk that came before Dr. Raju's talk, that very nicely set up the stage for the introduction of my talk. So we know that quantum computing is superior to classical computing. However, it is very brittle. It is very sensitive to noise. Back in the day, physicist DiVincenzo, he listed 7 requirements for a practical quantum computer. And out of the 7 key points that he set out, these 3 issues are, I would say, the most important issues, and also some issues that I kind of address in my talk here. So the first issue is the issue of decoherence. So this is basically when you prepare a quantum state, a qubit, it is always, it is never really isolated. So it's always interacting with the environment. And so the quantum phase information in the qubit can essentially decay because it will get somehow messed up by the environment. Next comes fidelity. So this is basically the accuracy to which logical operations, quantum logical operations and quantum gates can be applied on the qubits in order to manipulate quantum information. And we can't do that with perfect accuracy. It would have been great. And then the third issue is the scalability of quantum computers. We can't really do much with just one qubit. We have to scale things up and get in maybe a few hundreds. There's a very important rule of thumb threshold theorem, which basically says that the threshold for fault-tolerant computation is 10 to the minus 3, assuming that the noise is, say, depolarizing a photon. And what this theorem essentially says is that when you have some qubit system, there is going to be errors. There's going to be some kind of decoherence. There's going to be some physical errors. However, through some error correcting algorithm or some error correcting principle, you can correct for those physical errors faster than they're generated, so that it doesn't affect the logic of the computation. And this is an excerpt from a popular science magazine. So you can see that there are a lot of companies that have jumped into the picture of quantum computing, the quantum computing market. It's mainly in the Americas, but there is a few in Middle East as well as in Asia Pacific. And these are the different kind of hardwares that are being used for implementing the quantum computation. So the most popular one is by far superconducting qubits, and companies like Google, IBM, Rigetti, Intel, they are the main players here. There's trapped ions, there's photonic systems, there's computing with neutral atoms. There's also silicon-based devices using defects in silicon, etc. There's Intel in that. And then in the other ones, the key player is Microsoft. And this basically is the arena for topological quantum computation. And I'm going to be talking entirely about this arena here. So if we were following headlines, we know that Google and IBM have been making huge news in the past 2 or 3 years. So Google has just announced quantum supremacy with a 53 working qubit Sycamore processor. So quantum supremacy or quantum advantage is basically when you can provably show or demonstrate that a certain algorithm, if you if you run it on a quantum computer, it is basically exponentially faster than what you could achieve with the best algorithms from classical computing. It could be exponentially faster, and it could just be problems that are not even solvable in any practical sense. So Google in its Sycamore processor had 53 qubits, but then one wasn't working, so they had 53 working ones. And in this figure here, there's like 53 cross marks for the 53 qubits. And in the architecture that they put forward, every qubit was connected to 4 neighboring qubits. And so those are the dashes. So 4 neighbors for every qubit. And this plot is the error heat map that they got from their simulations. So the crosses mark the accuracy to which they could perform single qubit operations. Dr. Raju had mentioned this in his talk. And then the dashes are the accuracy to which you can perform double qubit operations. So connecting, say, this and that, etc. And you can see that for most of it, it's mainly between 10 to the minus 3 and 10 to the minus 2. So quite near the threshold here. And if we look at the growth in qubit count, then we see that there's a remarkable progress from IBM and Google, and they have almost reached 100 qubits now. And many apart from these leaders will be on the same path pretty soon. So my question to you is that, are we done? Is it just an issue of engineering, that we need just better hardware, just better engineering, more precision, and we would be done? Being a theoretical physicist, I would argue that it's not the case. I would argue that today's quantum computers are analogous to the ENIAC, which was a revolution in its own merit when it came forward, being the first, I think, automatic electronic computer that could do a lot of stuff. But it was very ginormous. It had to be given kind of tapes and instructions, and it wasn't really elegant. So I would argue that the quantum computers today are quite similar to the ENIACs in the 50s that came forward. And so I want to ask, are there any more elegant paths ahead? And this is going to be the field which can provide a much more elegant path, I will argue, is going to be topological quantum computation. So whatever we do on the shoulder of the giants. So Frank Wilczek, a legend by all standards, he did a lot for asymptotic freedom and particle physics. But what's probably slightly less known is that he also coined the term anion, which is the quantum of my talk, so to speak. And his work on non-abelian gauge theories and anion superconductivity really opened up the arena for this field. Then there's the mathematician Michael Friedman, who's at Santa Barbara, and he did a lot of the theoretical work on the Poincare conjectures in manifolds that really helped open the field, because as we'll see very shortly, it is very rich in its mathematical structure. Alexei Kitaev from Caltech, he pioneered the different lattice models. He pioneered the toric code, just a very seminal figure. Steve Henry Simon at Oxford University, I was lucky enough to have him as my master's supervisor. He worked on, along with Das Sharma, Friedman, Chetan Nayak, he worked on topological phases of matter. He worked on the fractional quantum Hall effects. Sankar Das Sharma at Maryland, he's also been a very influential figure in condensed matter physics and in topological phases. And Wen from MIT, he used to work on string theory for his PhD, but then he shifted to condensed matter, and then he did a lot of work on string net mechanism, string net condensation, and I would read his papers a lot for my master's thesis. All right, so let's introduce anions now. So these are exotic quasi-particles. So these are not fundamental particles. as you'd see in particle physics, but quasi in the sense that they emerge from some substrate of condensed matter, and they have any exchange statistics. That's why they're anyons. We know of fermionic and bosonic exchange statistics. So it really comes down to the topological properties of paths that you would need to take in order to exchange particles versus the dimensionality of space in which these particles are living. So in 2D versus 3D, etc. So if we have a wave function of two identical particles at R1 and R2, and we apply an exchange operator or parity operator, it basically maps R1 R2 to R2 R1. It just swaps the labels. And we know that in 3D, if we do that twice, we're basically coming back to the same configuration, right? And so quite trivially, when we're doing undergraduate physics, we would just write down that there are then two eigenstates of the parity operator, plus and minus, corresponding to bosons and fermions respectively. But let's take a closer look. And here, let's take a closer look, keeping in mind the dimensionality. So if you're exchanging particles 1 and 2 twice, then in the reference frame of one of the particles, it is the same as taking particle 1 around particle 2 and back, keeping particle 2 fixed because we are in the reference frame of the second particle. Right, and so you again have another path. Let's say you construct another path, this black T naught, which is a trivial path. What I mean by trivial is that you can basically imagine that you're just deforming this this path, you're shrinking it down to a nothing, to a null path, to just a point. So that corresponds to doing nothing. In 3 dimensions, right? If this is happening in 3 dimensions, so for fermions and bosons, then you can imagine that you have this outer green path T1, and you're essentially kind of taking it from the plane and you're taking it out, and then you're just squishing it down, you're shrinking it down. And so in 3 dimensions, T1 and T naught, they are topologically equivalent. However, in 2 dimensions, so that everything would be constrained to lie on the screen of my laptop here. So you cannot topologically deform T1 and bring it down to T naught. You would have to insert a cut. You would basically have to cut the line and then kind of wrap it around and make it T naught. So the 2 paths are topologically distinct, and any arbitrary phase, complex phase, can be assigned to the exchange. So anyons therefore admit any unitary evolution on particle exchange. Evolution could be any complex phase, so just e to the I phi, some phase for a billion anyons, or in general, it could also be described by some unitary matrix U, so that exchanging the 2 is related by unitary transform. And note that fermions and bosons correspond to anyons, with just phi's being 0 or pi, respectively. Great. So now I'm going to formally introduce anyon theories and topological theories and show how you can do quantum computation with anyons. So I think the best way to really think of anyons is through diagrammatics. In mathematical terms, well-behaved anyon theory is a modular tensor category. I know I threw a lot of mathematical formulas in there, but really in mathematics, everything is defined by a set of properties that it needs to satisfy. So in order to constitute a modular tensor category, an anyon model should have the following properties. Firstly, it should have a fusion algebra. So there are certain particle types. So there's the trivial vacuum, which corresponds to having nothing at all. There's, say, anyons A, B, C, they're antiparticles, etc. And this forms a group. And now the following properties should hold. First, everything should trivially fuse with the vacuum, because the vacuum should not change anything. Fusing A and B is the same as fusing B and A. Then this is the distributive property. So fusing A with B plus C is the same as just distributing it over. This is the most important one, which is if you have 2 anyons, right? Think of it, you can also think of it as different charges. If you fuse two different anions A and B, it can give you a sum of, it has to give you a sum of different anions C. And this factor here, the coefficient here, is just the multiplicity factor. So when we fuse A and B, if we get more than one outcome, then the abelian, then the anion is non-abelian. If we get just one outcome, say for anion A, then it's abelian, otherwise it's non-abelian. And that again relates to having evolution under exchange being just a complex phase or a matrix, which is a higher dimensional transformation. Second comes the F matrix. So what is this? It's basically changing the order of anion fusion. So we take particles and we can fuse them together. What if we change the order in which we fuse the particles? So it's equivalent to changing a basis. So imagine you have an anion D, and it can disintegrate into three final anions, A, B, and C. So the same thing happens in both the diagrams here. And recall that this is actually very similar to diagrams that you would see from particle physics. So D could disintegrate first into C and some intermediate particle, anion I, and then I disintegrates into A and B, or we could first get A and then you get B and C. And the two diagrams are related by F matrix transformation. Next comes the exchange statistics of anions. So if you have a global label or a global charge, and you have two anions coming out of it, so A and B, what you can do here is that you can introduce a twist in your diagram. So physically, like having the particles go around each other, and then they wouldn't be identical, the two diagrams. They would be related by a transformation, the R matrix. This is very interesting, braiding operation. So the best visualization is to think of braids on a string. The key point here is that under crossings is not equivalent to over crossings. So imagine that everything was fixed to the plane of the screen here, and you in this diagram you would have an overcrossing, right? So this string is going over the other string, and in this diagram the same string is going under the other string. So this would be an overcrossing, and this would be an undercrossing, and they're not equivalent. And you can easily visualize it by just repeating this same process, right? So you have this, follow this string, it goes over and then over again. So overcrossing followed by another overcrossing. And here you have an undercrossing followed by an overcrossing. And they're not the same, because you could essentially just pull apart the two strings on this diagram and you could just unentangle them. They would come out. Whereas on this side, since it's an undercrossing followed by an overcrossing, it would lead to forming of a knot. And there aren't any topological you can't do anything locally here to separate the strings. You would have to essentially cut the strings in order to separate them. And related to the exchange statistics, swing factors, which is a phase factor on twisting a particle by 2 pi. So for bosons, nothing happens, and for fermion, you have a sign introduced. And this is, in general, you can define this for all anions, right? And quantum dimension, again, this should sound familiar from particle physics, kind of similar to normalizing different diagrams from particle physics. Here, it's the dimension of Hilbert space, which is associated with the particle. And diagrammatically, you can show that this is also the value of a loop of anion A. That's the quantum dimension. And finally, we have the very important topological S matrix. So essentially, it is the value of interlocked loops. So you have, say, loops A and B from before, but instead of having them separate, you just interlock them so you can't separate them out. And it's related to the spin factors. All right, so I'm just going to give you a very quick primer on quantum computation, because I thought there would be a lot of undergraduates in the audience, but I'm going to very quickly go over this because the previous talk covered it in quite good detail, I think. So we have qubits, which are the bits of quantum information, and essentially these are the encoding elements of quantum information, in general qubits or qubits. So for a qubit, it's a two-dimensional space, so you have two basis elements. For a d-dimensional space, you have d basis elements, and the general state would be some superposition of the basis elements. For n qubits, you would essentially obtain the basis states by tensoring all the individual basis elements. So, I1 tensored all the way up to In, where Ij belongs to either 1 or 0. And again, as before, the general state would be some superposition of the basis elements here, 2 to the n basis elements, and all the complex coefficients would be normalized. And already superposition and tensoring of Hilbert spaces provide a point of departure and supremacy over classical. That's great. Now you have bits of quantum information. You want to manipulate the encoded information using quantum gates, and you want to measure whatever you have at the end of your algorithm by measuring it through projectors. So the quantum gates, like classical logical gates, encode the quantum information. The quantum evolution is unitary, so all the operations that we would perform would belong to the unitary group U over 2 to the n. And for single qubit systems, the gates include the well-known Pauli matrices, so sigma x, y, and z. For instance, sigma x, in the standard basis, sigma x would act as a classical NOT gate, causing a bit flip. An interesting single qubit gate is the Hadamard, which is a superposition of x and z. And this basically corresponds to a change of basis. So mapping 0, 1 and rotating it by 45 degrees to the diagonal plus and minus. So once you have, these were all single qubit gates, but you also want to go beyond 1 qubit gates to create entanglement. You would need a 2 qubit operation. So they would be achieved by using control gates, in general CU. 1 qubit would be your control, and the other qubit would be the target that you want to induce some transformation. So when the control is in qubit state 0, the qubit is left invariant, whereas when the other qubit is in the orthogonal state, the target evolves by unitary U. So just when U was X, we have the control NOT gate, and this is basically projecting to state 0, and you do nothing. Then the orthogonal state 1, and you just cause a bit flip. And in the standard basis representation, this part would correspond to when the first qubit is in 0, and it's the identity matrix, so you do nothing. And in this part, when the control is in the orthogonal state 1, you're basically flipping the target. And using a CNOT gate, you can generate entanglement between qubits. So if you have a in the control, if you have a superposition of 0 and 1, so that's the plus qubit, and then you tensor it with a 0, then that would generate the maximally entangled bell pair, because 0, 0, you do nothing, so 0, 0 over here, and 1, 0, since it's 1, you cause a bit flip, so 1, 0 maps to 1, 1. So you have the maximally entangled bell pair. Another example would be if you want to manipulate the relative phases between qubits. So if you apply the Z as a unitary, then it would change the relative phases of the target qubit. Finally, you have projectors for measurement when you want to project down to a certain subspace of the Hilbert space. So this is basically collapsing the wave function. And projecting twice is the same as projecting once, because you're already in the same subspace, and the product of projectors follows the Kronecker delta. For instance, if you want to project to the state ket 0, then you basically perform this ket bra, and that would be the standard basis representation, and that would project it down to the state 0. All right, with that, just one more thing, quantum circuit model, although I think it was mentioned in the first talk. So there are different models of quantum computing, but the one that I find most helpful for designing algorithms is the circuit model. So you have a series of quantum gates which transform your input qubit system to the desired output. And the net composition of the gates that you have, it forms the quantum algorithm that you want to implement. So for instance, you initialize everything, let's say, as everything zeros, and you have a circuit diagram like this, just arbitrary gates, for instance. So gates U can act on just a single qubit. So like locally, you're causing some transformation, or you could have double qubit gates, which would have 2 lines as input, 2 lines as output, for instance. So it would be manipulating these 2 registers and so on. And all these gates would act in succession, and time would evolve from left to right. And this implementation leads us to universality, which is basically you want to, given some qubit, you want to realize any arbitrary quantum algorithm. So psi naught, you want to map it to any arbitrary qubit state with some arbitrary unitary. And from a theoretical perspective and also from an engineering perspective, you want to minimize the number of gates that are being used. So essentially, you want to find the least minimal set of gates that will do the job. So a basis which will densely cover the entire set of possibilities of gates, so UN. And if you're interested, you can read up on these 2 papers. They're really good. Introducing the whole notion of finding this gate basis, and that will densely cover the space you want. For instance, if you just have arbitrary 1 qubit gate and you have the maximally entangled C naught, then that's enough for generating universal quantum computation for, say, a 2 qubit system. All right, and then now we'll enter quantum computing with anyons. So I talked a lot about the statistical properties through the diagrams of 4 anyons, and these are the very statistical evolution properties that empower quantum computing. So what is the analogy between the circuit model and, say, anionic computation? So and let's look at these things together. So if you're initializing a state, so just a bunch of registers in some kit, so that's similar to like initializing, say, the vacuum state, and then a bunch of anyons, different particle types, say E1 through E6. And then we want to basically apply different logical gates so that the answer so that we can massage the answer into probabilities at the end of our algorithm. So implementing quantum gates is equivalent to braiding anyons that I introduced before. So suppose you just let this evolve, you don't do anything with this particle anion. Here you kind of do an undercrossing, then an overcrossing, maybe then another undercrossing, etc. So all these elements here correspond to different logical gates, U, V, W, etc., that we're implementing. And then finally, what we want to do is that we want to take the anyons, we want to fuse them, and we want to measure the overall charge that we get. So state measurement is analogous to detecting the anion charge. And the really important thing to note here is that all these operations, all the braiding of anyons, is invariant to smooth deformations of particle trajectories. So if I just kind of wiggle the lines around, that won't change the probabilities that I observe here. It would only depend upon the topological properties of these paths, like how the different strings are knotted around each other. That would only matter. And so because of this topological property, error correction is intrinsically present in this system. And just a very quick example about a teleportation circuit with the Ising model. So the Ising model has 3 particle types. So you have the vacuum, you have the non-abelian anion sigma, and you have a fermion. And you have certain fusion rules. So the sigma is a non-abelian anion, which means that if you fuse it with itself, it would give you two fusion channels. So if it has any fusion process where it gives you more than one outcome, then that anion is non-abelian. Here you get that in this fusion, and you get the vacuum plus the fermion psi. This fusion rule basically tells you that sigmas can absorb fermions, and fermion is its own antiparticle. So fusing it twice gives you the vacuum. So sigmas have two fusion outcomes, one going to vacuum and the other going to psi. And with this, we can already implement a teleportation circuit. So imagine that you start with an overall psi, and let's say, so here you have nothing, just the vacuum. From psi, you can get two sigmas, and from nothing, you can also get two sigmas because of these two fusion channels. And then what you can do is that you can braid the sigmas around each other and then fuse them back, right? So because of this braiding operation, because of this logical operation we performed here, this fusion outcome now gives you the vacuum, and this fusion outcome now gives you the fermion psi, and times flowing, say, downwards. So only the fermion parity is conserved, and we have just teleported the fermion psi. So that's pretty great. And one more point here, which is the stability of anionic computation. We'll see this explicitly in a model, but as I briefly said, that the point to remember here is that grading anions and these particle trajectories, they only depend on the topology of the paths, and the topology of paths does not care about local deformations or smooth deformations that can occur from noise, from error from the environment. And the topological data that I introduced, like the F, the R, the S matrix, the topological spins, etc., those data, those are discrete, in the sense that if you if you perturb those values, you're not going to get another anionic theory. So this also provides an inbuilt kind of rigidity, the so-called Okinawa rigidity. Now let's introduce the toric code formally and see how it can do error correction. So the toric code is the simplest quantum double model. Kitaev introduced this in 2002, and it's based on the very simple Z2 group, which is just has two elements, 0 and 1. And you can write it down as a Hamiltonian on a lattice. So spin half particles on a lattice with some toric boundary conditions. So let's say you have some rectangular or square lattice, and you basically identify the parallel edges, and doing that basically maps a square or a rectangular lattice onto a torus. So basically glue the parallel edges and you have a torus. And the Hamiltonian is defined in terms of these vortex and plaquette operators. So you have, let's say, spins on the lattice, and you have this vortex V or nu and this plaquette P. And the Hamiltonian is just a superposition of all the different vortex and plaquette operators. So vortex and plaquette operators acting on all the qubits. And as we'll see in the next slide, these are all operators that act on neighboring four spins. So the vortex operator here would act on 1, 2, 3, 4, and this kind of square thing is the plaquette, and this would act again on 1, 2, 3, 4. So what is the nature of the operators? These are all Pauli spin operators, and these are just product of sigma x's acting on the four spins or sigma z's acting on the four spins. And every plaquette operator or vortex operator obviously commutes with each other, because sigma x's commute with sigma x's and sigma z's do the same. But also what's more interesting to note is that these things also commute between each other, right? And if everything if you can write down a Hamiltonian where everything commutes with everything, then you can basically write down, you can explicitly solve your Hamiltonian. To see the non-trivial case where a nu commutes with dp, right? Consider the lattice and consider these two operators. So you have the vortex and you have the plaquette. So whenever they don't touch each other, they will obviously commute because they're acting on different spins. But if they overlap, right, they would always overlap on an even number of spins. So either 0 or 2 spins, right? So if you just take this and you bring it over here, then you would see that this spin and that spin would be common to, this spin and that spin would be common to both the operators. And we know that, one sigma x and one sigma z anti-commute. So if you have an even number of such overlaps, then you would always have commutativity. All right, so with that, you can exactly solve the Hamiltonian, and you can write down what's the ground state space and what are the excited states. So each operator would have 2 eigenstates, plus or minus lambda, plus or minus 1. And operators would favor even up spins, right? Because you have a 4-spin interaction. So it will always favor up spins, even up spins, or even down spins at each vortex, and consequently at each plaquette. So there's a convention that you could say join from here, you could just join the up spins, right, by a string. And then the ground state would be formed of closed string loops. And so this would be, say, a closed loop with all, say, up spins. And the eigenstates, you can work this out, would be superpositions of flipped and unflipped loops. So what do I mean by this? So if you have this configuration as a closed loop, right? It's a closed loop. And then you basically apply a flipping operator, which you basically say apply it here on this plaquette, right? Then you basically flip this spin and that spin, so they don't enter the diagram. And this spin and corresponding that spin are now flipped. So they are now up spins, and now they appear in the string label. So you just kind of, from here, you map it to this diagram. So basically, if all the different loop configurations are flipped and unflipped, then they are eigenstates, right? And applying, that's what I said, applying the vortex operators would flip the loops, but loop states would still be mapped to loop states. All right, so with that, we can talk about excitations in the toric code. So excitations appear whenever the operators are violated. So occurs when you have an operator, the vortex or the plaquette, and it gives you, on psi, gives you minus psi. So that's an excitation. If you have defects on the vortices of the lattice, then those are E anions, or the electric fluxes, and plaquette defects are magnetic excitations or magnetic fluxes called the M anions. And they always come in pairs, right? Because if this spin is, say, a down spin, so if we apply a plaquette operator, a vortex operator at this vortex or at this vortex, then since there is an odd number of up spins or down spins, it would violate the operator, and then the excitation, the E anionic excitation, is said to live at the vortices where the operator is violated. So at these two, similarly, if you have the plaquette operator being violated, then at this plaquette and this plaquette, then the excitations come in pairs and they live at the plaquettes. So these excitations, or these defects, are actually abelian anions. So if we now turn to the anionic picture of the Hamiltonian, we first have no excitations, ground state, everything is great. You then have the vortex defect, you have the plaquette defect, and also you can combine a vortex and a plaquette defect, right? So just imagine bringing these two together, and then you would have a composite or a fermion. And E and N are abelian anions, where epsilon is a fermion. And again, if it's an anion theory, then it would follow some fusion rules. So the fusion rule here is that if you take anything and you fuse it with itself, it just disappears to the vacuum. And you could think of this because it's based on the Z2 group. So if you take anything in the Z2 group and you fuse it with the same thing in Z2, then 0 times 0 is 0, and 1 times 1 is also 1 plus 1 is also 0, right? So that's why you have these three rules. And here it's basically saying that if you have, say, an electric and a magnetic composite is the fermion, and from these rules you can derive that whenever a fermion is absorbing an electric or a magnetic flux, it is giving you the other flux because of the Z2 property. And exchange statistics. So the anions have trivial self-exchange statistics, so they are bosons, but they anti-commute with each other, and everything anti-commutes with the fermion because it's a fermion. And just from this, you can write down the topological S matrix, what I introduced before. And let's not go there, but basically for E anions, right, it commutes with itself, but it anti-commutes with the M and with the fermion. M commutes with itself and obviously vacuum, but it anti-commutes with E and anti-commutes with the fermion, etc. So error correction. The toric code is an error correcting code. And what do I mean by this? So let's again look at how errors were generated. So if we apply, the vacuum state, everything is fine, and we apply sigma x Pauli operator, then we create the error string, right? So the E anions live at the ends of the string, and now we can keep on applying the sigma x's, and we can let the string grow in length, right? So instead of here, it just goes onto two units here, and the E anion is transported up to here. And similarly, it can basically propagate through the lattice. However, the important thing to note here is that all these errors are topologically equivalent to the trivial state, because you have not really done anything, in the sense that because it's a topological model, and we only care about the topological paths of taken in the theory, we can easily contract these loops. We can smoothly apply local operations and smoothly contract the loops to the trivial state. And only non-contractible loops around the torus handle is significant. So what I mean by this is that suppose this picture, you map it onto the torus. So you have the ends of the E anion here, and this is the string, right? And the thing to note here is that errors are random, right? We are not, engineering the errors. It's just interactions with the environment. So the E anions have to basically, there's a chance that they will basically kind of come back, and they would fuse with each other, and they would just go back to the vacuum. But there's also a chance that they would go around the torus, right, leading to a topologically non-trivial loop, non-contractible loop, and that would be a different state. And those errors would be actually significant errors. However, the energy penalty in getting those errors would grow with the system size, and so this gives you inbuilt topological robustness. So that's the error correction. And when we know what the ground states are, then we want to know how we can encode information and how we can manipulate the same quantum information. So what is the logical qubit space in the toric code? So all the ground state space are closed loop configurations from before. And that gives us 4 topologically distinct ground states. So this is basically when there is an error, and the error propagates around this handle, or there's another handle over here. So either this or that. And then there's another situation where you can have a superposition of both the errors along both the handles. And these are the 4 ground states, because again, these are all closed loop configurations. So it's a ground state, but they are topologically distinct. And to go from one state to the other, you can now just apply these loop string operators, which can take you between the different ground states. And having these operators that can take you between different states is giving you the qubit evolution. So you can implement some algorithm now. And just a final note on the toric code. So I just introduced the Pauli operations. Everything was sigma x, sigma y, sigma z. So it cannot support universal quantum computation. You would need some defects. You would need some deformations called twists in order to support universal quantum computation. But that has been also studied in the Target code. So now I'm going to introduce a very famous model, a very simple but very elegant model that can support universal quantum computation. This is the Fibonacci model. It is just has two particle types. There's the vacuum and the tau, the Fibonacci anion. And these are the fusion rules. And if you look at, so the first fusion rule is very trivial. So the tau fused with the vacuum gives you tau. And this is the main fusion rule, which tau fused with itself gives you again vacuum plus tau. So as tau has more than one fusion channel, it is a non-abelian anion. And this fusion rule, right, already gives us the dimension of tau. So if you just take the dimension of this equation, right, so dimension of tau squared is 1 plus tau. Solve this equation, you get the dimension as phi, which is the golden mean, and hence it's called the Fibonacci anion. And now you can think of, taking a system of n such Fibonacci anions and fusing them together to find the dimensionality of the associated Hilbert space. So a diagram something like this. You have a set of tau anions and you fuse them, you get some intermediate state, either the vacuum or tau itself, and you have such an n kind of system, and in the end you get tau. And with this, you can get that the dimensionality of the Hilbert space follows the Fibonacci sequence. So that is very interesting in itself. And a number theoretic result is that the dimension of the model that grows exponentially with phi to the n. Now the promise for universal quantum computation on the Fibonacci model. So recall the F and R matrices that we defined before. So you have the R matrix where you have two tau anions going in, and you also have, say, an overall tau particle, and that disintegrates into 3 taus, right? And that gives you the F matrix, and this gives you the R matrix. And already just with these two F and R matrices, you can construct some unitaries. So first of all, what are the qubits that you would need? So qubits are these two logical qubits, so 0 and 1, so living in SU2. So one channel would be when the two taus fuse to the vacuum, and the other channel would be when they fuse to the Fibonacci anion. And the braiding unitaries that you have, B1 and B2, so basically you take R and then you transform R with F, and you act with these two unitaries, you act on the two logical qubits, and you can show that this density covers SU2, which is the qubit space you want, with an accuracy, with an arbitrary accuracy epsilon. And you can generate these two logical qubits starting with 4 anions. So T1, T2, let's say, for encoding one channel, and T3, T4 for encoding the other channel. And 2 logical qubits. So basically, for n logical qubits, therefore, you just need 4n physical anions, and you will be done. You can implement any arbitrary quantum algorithm on the Fibonacci model. So that's great, but one thing that's really difficult is that it's very, very difficult to realize the Fibonacci model. I don't think anyone has even done it experimentally. There's been a lot of proposals how you could realize the Fibonacci model on other anionic models and introduce things like defects, things like twists, and maybe you could realize or approximate the Fibonacci model. So this brings me to the final chapter of the talk, which is boson condensation in layered TQFTs. So first of all the different theories that I talked about, these anionic theories, these are all TQFTs, so topological quantum field theories. And basically the thing is that certain TQFTs admit bosons, and if you condense bosons, you can induce phase transitions in these theories. And so what does it mean to condense a boson? So the mental picture should be, think of a Bose-Einstein condensate, and this is the visual picture here. So basically the boson comes for free and the boson number is not conserved. And this picture is due to Levin-Venn as a mechanism of string net condensation. So think of, these objects called strings, right? And, think back to the strings that I was drawing on the toric code, right? And these strings have two competing forces. So a kinetic term and a potential energy term, right? And if the ratio is much greater than 1, then the entire lattice can be just filled with these string nets. So it would be string net condensed. And so why do we care about boson condensation? So firstly, the world is 3+1 dimensional, and the bulk phases with topological order, they do not have a systematic understanding as of now. And phase transitions between these anionic theories can provide insights into bulk phases. And what's also very interesting is that you can generate Majorana bound states in through twist defects in codes such as the toric code, and then and the Majorana bound state is a very first of all, Majorana particles are very elusive, and there's been a lot of work on, say, hybrids between Majoranas and junction superconductors and things like that. But studying phase transition could provide insight into all of this. So formally, if you want to study phase transitions, we have some theory, some anion category, let's say A, and there are different bosons in category A, and we want to condense it to a new category T. So what basically happens is that you have some particle in your original theory, and then that gets restricted or mapped into a sum of different particles in your new theory via some coefficients. And going the other way, if you have particle T, anion T in your new theory, then that gets lifted into sum of particle A in your original theory. And so this basically illustrates that you start off with some theory, and then maybe you could directly you have some tensor, you have two copies of the same theory, so a layered structure of anions, of anionic theories. You project it down to a single theory, and then you restrict to, or you do the condensation to go to the new theory, or you could first condense in both the layers or n copies of the theory, and then you could project down to just one copy. However, what's really interesting is that you can have models where there are bosons, but they do not admit any sort of condensation. So you can't have a phase transition via a boson condensation. And there's a really cool result on a Noble theorem that basically states that a boson cannot condense if the sum of the quantum dimensions associated with its zero mode set exceeds the quantum dimension of B, right? So this is just that in equation. And essentially this is similar to conserving energy mass energy in particle decays. For instance, we looked at the Fibonacci anionic theory, and if you take I think 5 copies of the Fibonacci model, or multiples of 5, you get bosons in your model. However, if you try to condense that particular boson, you cannot, the theory cannot undergo boson condensation. So basically, I would like to end there by just saying that this field of topological QFTs and topological quantum computation is beautiful in its own merit, and it deserves investigating. It is potentially a much more elegant path towards quantum computing. So, maybe it's true that in the near term, quantum computers, we will have, superconducting qubits and, other forms of quantum computation. But this would be a much more elegant path, which would require, not that much of resources. It is true that it is, first of all, very difficult to get the anions, because remember that these are quasi-particles. They do not fundamentally exist in nature. But once we have, ways to create these anions, then from there onwards, it will be very, very elegant and very easy to construct powerful quantum computers with probably universality. And studying phase transition in particular could be fruitful in realizing these difficult to achieve topological phases, and it can also provide insights into bulk phases. And I would just like to end with this quotation from Das Sarma. He says that topological quantum computation does not try to make the system noiseless, but instead it makes it deaf. So you don't have to explicitly kind of have 1,000 or 10,000 physical qubits in order to prepare a system that has 10 physical or 100 physical qubits. The system itself has this built-in robustness, and so you don't have to try to make the system noiseless. It has this built-in immunity to errors. These are some of the references I've used, so feel free to take a look into these resources. And with that, thank you. I'd like to take any questions, and also I'd be happy if you want to connect with me on LinkedIn, and I'm always kind of happy to kind of provide kind of resources or insights into, for undergraduates for if they want to do projects and such. So with that, thank you.
Thank you, sir. Thank you for your wonderful presentation. And we'll see, sir, very good the feedback we are getting from the participants from YouTube as well as from this the chat box, sir.
Right, I'm just trying to pull that up.
Yes, sir. Yes, sir.
Maybe if I stop sharing.
Yes, sir. There are very nice feedbacks from participants, like knowledgeable session, nice session, informative presentation, like that we are having the feedback, sir. Yes, thank you, sir. Thank you for your the valuable and informative sessions, presentations. Thank you so much, sir, once again. Thank you, sir. Thank you.
Thank you.
Now I request Dr. Jagdish V. Angadi to take the chair for this oral presentation of the participants. Now over to Jagdish Angadi, sir.
Thank you, Mr. Santosh. Good afternoon, all. Let's begin the oral presentation. First of all, I will thanks to organizing committee to giving this opportunity. All the participants strictly stick on to the time limit for the presentation, that is 8 + 2 minutes. And let's begin our oral presentation with Ms. Sulakshana, NIT, for present her work. Kindly unmute yourself and start our presentation, Sulakshana madam. Ms. Sulakshana.
Hello.
Kindly unmute yourself
Hello.
and start your presentation.
A very pleasant good afternoon to all present here. I would like to thank the organizing committee of the conference for providing me an opportunity to present my research work. Today, I shall briefly discuss on the topic a robust photocatalyst using silver quantum clusters grafted in titanium dioxide nanotubes. The outline of the work mainly consists of the challenge of the 21st century, a comparison between metal nanoparticles versus metal quantum clusters, silver quantum clusters embedded on TiO2 nanotubes, followed by results and discussion, and finally conclusion. As you can see from the slide, water pollution caused by the release of toxic chemicals, including dyes, pharmaceutical and personal care products, is very critical to environmental problem. These hazardous colored effluents are usually discharged from industries such as textile, rubber, and paper. The exposure of these organic pollutants into the water body has adverse effect on the aquatic organisms. Although there are various conventional techniques for water treatment, most of the dyes are very stable and non-degradable. Hence, the complete removal is not achieved as they produce some toxic byproducts. On the other hand, among the advanced oxidation processes, photocatalysis ensures the complete mineralization of contaminants. The process mainly involves in situ generation of highly reactive transitory species, namely hydroxyl radicals and superanion radicals, for the complete mineralization of dyes into carbon dioxide and water. As we know that TiO2 itself is a prospective material for photocatalysis. But the only limitation in TiO2 is that it can only absorb UV light, which consists of only 5% of the solar spectrum, and the major portion of the solar spectrum consists of visible light. Hence, it is necessary to sensitize TiO2 with visible light active materials. So now here I shall discuss about the metal comparison between the metal nanoparticles versus quantum clusters. So in the work that was presented by Sridharan et al., they have synthesized silver nanoparticles and silver quantum clusters. As you can see from the absorbance spectra, the metal nanoparticles is showing a strong absorption peak at around 390 nanometer. This is because of the collective oscillation of the electrons occupying the states near the Fermi level, leading to a phenomena called as surface plasmon resonance. Whereas if you see the absorbance peak of silver quantum cluster, there is no strong absorption that is taking place. This is because of this quantum confinement effect. For when size of the nanoparticles varies and large number of metal atoms are protected by organic ligand, it forms a metal quantum cluster which are non-toxic and environmental friendly. So it has attracted in the field of environmental remediation. So now the present aim of this our work is to synthesize silver quantum clusters embedded on titanium nanotubes and to investigate their photocatalytic activity for the organic pollutant degradation. For synthesizing titanium dioxide, we have followed the procedure published in Crystal Engineering Communication by Sridharan et al. Thornball nanostructures of titanium dioxide were first synthesized through hydrothermal approach, reported previously. For fabricating the one-dimensional titanium nanotubes, the obtained structures were treated chemically under alkaline hydrothermal conditions. Synthesizing the quantum clusters of silver, they have used solid-state route under room temperature conditions. For embedment of silver quantum clusters over titanium tube, dropwise addition of silver quantum clusters into ethanolic solution of titanium nanotubes resulted in the precipitation formation of the composite. The XRD patterns of titanium nanotubes show that nanostructures of titanium tubes are clearly formed And the quantum clusters of silver show the FCC structures at around 111 place. Morphology and chemical composition of the as synthesized photocatalyst were characterized through FESEM, EDS, and TEM. So from the figure A, we can see that the nanotube morphology of titanium dioxide nanotubes is visible, while the presence of silver quantum clusters embedded over it is not visible because of the very low resolution. Whereas from the EDS spectra, it is clearly visible that both silver and sulfur percentages were present, meaning that the silver quantum clusters are embedded over the surface of TiO2 nanotubes. UV visual absorption spectra of titanium nanotubes shows strong optical absorption in the UV region and weak absorption in the visible light region. On the other hand, in the increase in the absorption in the visible light region confirms the embedment of silver quantum clusters in titanium dioxide nanotube. So top plot of the photocatalyst shows that the band gap of titanium dioxide has drastically reduced from 3.1 to around 2.25 electron volt. Meaning to say, the silver quantum clusters are sensitizing titanium dioxide to absorb the visible light. The visible light driven photocatalytic degradation of organic pollutants were carried out for the degradation of two azo dyes, namely methylene blue and rhodamine B. From the time degradation plot, it is very clear that the silver quantum clusters, titanium dioxide, is taking lesser time to degrade the pollutants in comparison to pristine titanium dioxide. Chromium-6 is another toxic carcinogenic inorganic pollutant and it should be removed from water. The plot of chromium reduction against the irradiation time is also shown in the figure. Approximately, silver quantum cluster titanium dioxide has taken about 180 minutes to reduce 33% of the chromium. And again, the strong confinement effect in silver quantum cluster enables it to exhibit multiple molecular like single electron transitions, leading to the wide absorption of the visible light region. And also due to the formation of the heterostructure between the silver quantum clusters and titanium dioxide, there is improvement in the separation efficiency of the charge carriers formed. So therefore, in the conclusion, silver quantum cluster titanium dioxide nanotubes were successfully synthesized. The silver quantum cluster had a wide range of absorption in the visible light and they acted as a sensitizer for TiO2 nanotubes and they exhibited good efficiency in the photodegradation of organic pollutants and for the reduction of toxic chromium-6. Thank you.
Thank you, Ms. Sulakshana. Any questions from the participant side? Any questions? Okay, I have one question, Ms. Sulakshana.
Yes,
What do you mean by dark absorption?
Sorry?
What do you mean by dark absorption?
Dark absorption.
Yes. As you mentioned that irradiation time is as increasing the irradiation time, dark absorption is decreasing with increasing the irradiation dose or time. What do you mean by that dark absorption, please?
I didn't get you, sir. Dark absorption.
Dark absorption. You mentioned the graph actually. I've seen the graph.
Sir, can you see?
Dark absorption.
Oh, okay. You mean to tell dark adsorption. Okay.
Yes.
Dark adsorption means initially what we do, we take the dye molecules
Yes.
and prepare the aqueous solution out of it. And then allow the photocatalyst to get adsorbed. And we allow it to stir for 30 minutes in the dark so that the pollutant will get adsorbed over the surface of the photocatalyst. So that is known as dark adsorption.
And why it is found to decrease with increasing the radiation time? What is the main reason of behind that?
So one thing is, if you see the titanium dioxide alone, so it is taking nearly 210 minutes for degrading methylene blue as well as rhodamine B, because it cannot absorb visible light. It can only function in UV light. Whereas when silver quantum clusters were added along with titanium dioxide, the band gap of the titanium dioxide has reduced, because of which it can absorb the visible light. And also this quantum clusters, there is a heterojunction formed between the quantum clusters and the titanium dioxide, because of which there is the recombination of the charge carriers also has reduced, and because of this it is showing good activity.
Okay, nice presentation, Ms. Sulakshana. If there is no question, we'll move for the next presentation. Thank you once again. Dr. K. Kumar, Department of Post-Graduation Studies and Research in Physics, St. Aloysius College, Mangalore. I will just hand over the session. Dr. K. Kumar, please. Dr. K. Kumar.
Yes, sir, I'm here, sir.
Yourself and start your presentation, sir.
But I can't share my PPT here. Can you help me?
Please stop sharing your screen. Ms. Sulakshana, please stop your sharing the screen. Sulakshana. Ms. Sulakshana Shoni, please stop your sharing the screen. Okay. Now?
Yes, sir.
Yes, sir. Please start your presentation.
Yes. So good afternoon to all of you. Before I begin my presentation, I would like to thank Dr. Rajesh Nairi, convener of the conference, also the college, giving me an opportunity to present some of my research work here. So my oral presentation's the title of my oral presentation is Green Light Emitting Nitrogen Doped Graphene Oxide as a Fluorescent Sensing Platform for Efficient Detection of Copper Ions. So outline of my oral presentation as follows: introduction, preparation of nitrogen doped graphene oxide, characterization and detection of copper ions using nitrogen doped graphene oxide. So graphene oxide is the oxidized form of graphene that is commonly prepared by the Amos method. So W.S. Amos gave the method for preparing graphene oxide in 1958. And later, recently in 2013, this method is modified by eliminating Na2SO4. Graphene oxide comprises mainly three important functional moieties such as carboxyl, epoxy, and hydroxyl functional groups. Therefore, because of these functional moieties, graphene oxide can be water dispersible. Therefore, it is a very suitable candidate for biomedical applications. So this is the proposed structure of graphene oxide. And here you can see the important functional moieties just now I mentioned. This is a carboxylic acid. So this is a hydroxyl, OH is the hydroxy group, and we have a epoxy group. In addition to these functional moieties, also we have conjugate structure, alternate double bonds here. Also we have, this is due to sp2 hybridization of carbon atoms. Also we have here epoxy group, and this carbon, particularly this carbon formed from sp3 hybridization of carbon atoms. So here we can say graphene oxide is a mixture of sp2 and sp3 hybridization of carbon atoms. And if you study the optical band gap or electrical band gap of these materials, graphene oxide, you will find more than 4 electron volt. An important thing is here, if you take a graphene, since graphene has a 0 band gap, and there you can see there is no electronic transition between any energy levels, because optical band gap is 0. But after oxidizing the graphene, that means we are introducing oxygen moieties or oxygen into the graphene structure. As a result, we can get some electronic band gap in the material, say graphene oxide. Therefore, electronic energy transitions here are responsible for the fluorescence of graphene oxide. This is reported in this article. And also we can effectively modulate the electronic structure of graphene oxide by introducing dopants such as nitrogen, fluorine, boron, etc. So doping also affect the fluorescence emission of graphene oxide. The effective dopant to the graphene oxide is nitrogen, since nitrogen has non-bonding electron of lone pair of electrons. In nitrogen doped graphene oxide, the fluorescence is dominated by N2 pi star transition between the aromatic rings that contain nitrogen and the conjugate structure of graphene oxide. As I told you just now, nitrogen has non-bonding electrons, okay, that contribute to this transition, N2 pi star transition. If you take the carbon-based materials such as carbon darts, graphene quantum darts, carbon nanotube, etc., including and graphene oxide, so these are very attractive fluorophores that are inexpansive, non-toxic, photostable, and environmental friendly. So these are the important characteristics of carbon-based materials, which are very suitable candidate for particularly bio-related biological applications. This graphene oxide, here I'm just focusing on graphene oxide. Graphene oxide is one of the, we can say, it's a derivative of graphite. And this graphene oxide can be taken as a fluorophore as well as a quencher. So if you are using graphene oxide as a fluorophore, you can use it for fluorescent biosensors. If you're using quenchers, you can also detect some metal ions which are present in some water or any other solutions. So my aim of this work is to use this effective use of graphene oxide in detecting copper ions. So the preparation of nitrogen doped graphene oxide is very simple. It is an extensive work of this Yang Dong et al. Carbon, which is published in Carbon Journal in 2012. What they did, they used just citric acid and they decomposed this citric acid at elevated temperature. That is above the melting point of this particular compound, citric acid. What we did, we added this urea. Here, urea is taken as a nitrogen source because we are focusing on this doping N into graphene oxide. We have taken equimolar ratio of citric acid and urea and heated at elevated temperature, say at 190 degrees Celsius for 2 hours, and we obtained this nitrogen doped graphene oxide. And we confirmed the structure of nitrogen doped graphene oxide by various characterization techniques. The important characterization technique is to investigate graphene oxide, is Raman spectroscopy. So this figure shows a Raman spectrum of nitrogen doped graphene oxide. And this is a publication in Optic in 2019. Here you can see two prominent peaks. One is G mode and another one is D mode. This particular G mode, this G peak arises in this kind of graphene oxide. This is the omnipresent G mode. It's the only Raman active E sub 2G mode at the brilliant zoom center. And this symmetry mode restricts the carbon atoms to vibrate in plane in 6-member carbon ring. So this is the characteristic of all carbon-related material, particularly graphite derivatives. Also, we have another D mode. Before that, I will explain a little about this. So we have two types of Raman scattering. One is the first order Raman scattering and the second order Raman scattering. In first order Raman scattering, this is only for optical phonons, in which the photon wave vector, that is Q equal to 0, which is involved. But in case of second order scattering, suppose if the incident photon excites the crystal from initial electronic and vibrational state to a virtual state, and then the crystal emits a scattered photon and makes the transition from virtual state to a final electronic and vibrational state, which is different from the initial state by 2 vibrational quanta. Therefore, this kind of scattering process in Raman spectroscopy is called second order scattering process. Let me come to second order scattering process in a present case. So here we have, just now I told, a D peak. This peak is at 1355 per centimeter. In order for a D peak to occur or arise in graphene oxide, here a charge carrier must be excited and inelastically scattered by a phonon. Okay, there is a inelastic scattering between the charge carrier and a phonon, which is followed by a second elastic scattering by defect or zone boundary must to occur, result in recombination. So here, one important result we can draw here. Suppose if you take the Raman spectrum of just graphene, there we don't find in general this D peak because no defects are present in pristine graphene. Suppose if we introduce defects in graphene by oxidizing it, therefore defects are formed. These defects are identified by using this Raman spectrum. Therefore, yes, pardon?
Even 10 minutes, even start
yeah, sorry. Yes, so this is directly depends on the number of defects. This defect can be absence of some 6-member carbon ring or defects at the edges, etc. Also, we use EDX energy dispersive X-ray spectroscopy to confirm whether the dopant is there in the graphene oxide or not. And this is the EDX energy dispersive X-ray spectrum of graphene oxide. And here you can see, we know that carbon is rich in graphene oxide. After oxidizing, oxygen is present, and also we incorporated this nitrogen in the graphene oxide. Therefore, from EDX, we can confirm that nitrogen is present in the graphene oxide. And this is the FSM image of nitrogen graphene oxide. Yeah, and also we recorded the fluorescence spectrum of nitrogen doped graphene oxide with the help of ocean optics. So here one thing is this is how we arrange this is the experimental setup for fluorescence emission measurement using ocean optics. Here instead of this valence, this deuterium tungsten source, here we replace this source by ordinary light emitting diodes, and this is the optical fiber, and this is a sample. This is a sample holder, or it's a cuvette where we. This is sample holder where we placed our sample, and this is ocean optics sensor, and this is connected to the laptop where we install this ocean optics software. And this is how we measure the fluorescence emission of the compound. So using that data, we we plotted, this figure shows the spectrum plot with the rainbow under the curve at lambda excitation 452 nanometer. So this is the excitation wavelength we use to excite a graphene oxide. Okay, and this is the emission spectra, fluorescence emission spectra, spectrum of graphene oxide. Here we can see a multiple emission from graphene oxide. This is because, as I told you, graphene oxide contains several functional moieties such as carboxylic acid, OH, etc. So these are the origin for the emission spectra for graphene oxide. And this is the picture which we are taken by a mobile, ordinary camera using mobile. And now if you want to know which wavelength or which emission color is dominating out of this, and what is the purity of that particular emission. So this particular information we got using CIE diagram. So this is using CIE diagram, we could be able to locate the XY coordinate of this. So this is called a Ashore diagram in CIE 193 diagram. Along x-axis, this is the x coordinate, this is a y coordinate. So x and y coordinate value for this particular graphene oxide is here. And this is a reference somewhere here. And if you join these 2 points and extrapolate this line till here, and this line will intersect with the boundary of the Ashore diagram, that intersecting point corresponding to the dominant wavelength of the graphene oxide. For this graphene oxide, we got dominant wavelength is 527.8 nanometer. And the purity of this emission is 60%. And the final one is the detection of copper ions. To detect the copper ions, first we prepare the standard standard stock solution that is equal to 0.1 molar concentration. And the fluorescence intensity of the solution was recorded in the wavelength range of 200 to 800 nanometer with a fixed excitation wavelength at 452 nanometer. And I told you this is a LED, light emitting diode at 5 volts. Before detecting this ion, first we have recorded the blank solution. That means without adding copper ions. And later we added copper ions and measured fluorescence emission intensity of the solution. And this here we have taken the amount of NGO solution was fixed at 3 ml. So before the addition of copper ions, so all measurements were recorded at room temperature. So this is the measurement. This is the response we obtained. So this figure shows the fluorescence emission spectra of nitrogen doped graphene oxide. So 0 micromolar. That means in the absence of copper ions, the solution shows shows this emission, fluorescence emission, which is IS for for 0 micromolar solution. And as we increase the ion concentration, copper ion concentration in the solution, the intensity of the fluorescence intensity of the compound start showing, or it start decreasing. And we, around 11, this intensity falls very significantly. And as we continue to increase the copper ion concentration in the solution, say at 20 micromolar, and we recorded very less intensity for that solution. The reason for this, very simple. Here, the fluorescence of graphene oxide can be quenched by a charge transfer process in which graphene oxide acts as a charge donor. Okay, so this as we increase the copper ion concentration in the solution, the fluorescence emission intensity of ZO start decreasing. This is because of quenching process. Okay, during quenching, there is a charge transfer from GO to, we can say GO acts as a charge donor. And also, there is a strong affinity between graphene oxide, which comprise COH, carboxylic acid group, and OH group with these copper ions. Okay, there is a complex between these metal ions, copper 2+, and graphene oxide. So that will lead to the non-ready to recombination process. As a result, we can expect the decrease in the fluorescence intensity of our graphene oxide as we increase the concentration, copper ion concentration. And the interaction could originate from the electrostatic force, just now I told you, of graphene oxide and metal ions with the opposite charges. Okay, Similar work I have done in several researchers by using various metal ions such as mercury, cobalt, magnesium, etc. The conclusion of my oral presentation is from Raman spectra for graphene oxide, we indicated defect formation during the oxidation because in Raman spectrum, we saw there D peak corresponding to the defects in graphene oxide. And the green emission at 529 nanometer is dominated. This particular wavelength is dominated in the fluorescence emission spectrum with the color purity around 60%. And the fluorescence intensity of graphene oxide is quenched by copper ions. The main applications of this compound is metal ion sensors, biomarkers, and drug delivery. So with this conclusion, I conclude my oral presentation. I thank for your attention.
Thank you, Dr. Kumar K.
Yes, sir.
Any question from the participant side? Any questions? I have one question, Dr. Kumar.
Yes, sir.
I have seen in the Raman spectra so much of noise in the background actually.
Yes,
whatever
yes.
the absorption bands will be observed, Raman bands.
Yes, sir, correct.
Also, we have seen a lot of noise in the graph.
Here we have
behind that.
Here we use the raw data as it is. That's why we are getting a noise here.
Okay. No, is there any scientific background?
No.
That is depend upon the synthesis method. Whatever the synthesis method adopted by you, that is Hammer's method, right? That is depend upon that method, or
it depends on methods. Sir. Suppose if I prepare graphene oxide by using Hammer's method, you get, but the prominent peaks for graphene oxide is same. For if you synthesize graphene oxide using various techniques, these are the two prominent peaks, G and D. But the intensity of D will be different for different methods.
Okay. Okay, Dr. Kumar, nice presentation. If there is no question from the participant side, I would like to thanks to behalf of organizing committee, Dr. Kumar. I would like to thanks once again. Thank you, sir.
Thank you so much.
Now I will call upon P. Mathwes, Thin Film Research Lab, Department of Physics, St. Thomas College, Kerala. Sir, please present your work. J.P. Mathwes. Can you hear me?
Yes, sir.
Yeah, start work.
Very good evening to one and all present here. I thank the organizers to give me such an opportunity to present my work before all of you. Myself, Dr. Jabin from Thin Film Research Lab of Department of Physics, St. Thomas College, Pondicherry. The topic of my today's presentation is photoluminescence properties of cobalt doped zinc oxide thin films, role of doping concentration and annealing. Why I choose zinc oxide and TM doped or cobalt doped zinc oxide for my work? The answer is because of its unique properties of zinc oxide, such as direct and wide band gap, large exciton binding energy, strong nonlinear resistance, a high thermal conductivity, availability of large single crystals, radiation hardness, and also there is reports that the TM doped zinc oxide films shows a room temperature ferromagnetism, so it can be used as TM doped zinc oxide thin films can be used as dilute semiconducting devices, and also it can be used in magneto-optical devices. The next slide will show how the synthesis method of cobalt doped zinc oxide thin films. The molarity of zinc acetate and cobalt nitrate solution was kept at fixed at 1 molar. Both solutions are made in distilled water. The solution is then mixed with a 2.5 weight percentage of PVA solution. The solution is mixed by stirring the whole solution for 1 hour. Then we get a clear solution. The films are prepared by dip coating method. The coating was made on glass substrates. The substrate is dipped into the sol-gel solution with a withdrawal speed of 10 centimeter per minute and a dipping delay of 30 seconds. In order to remove the organic residuals completely, the obtained films were heat treated for 10 times at a temperature of 250 degrees Celsius. I select the temperature, heat treatment temperature as 250 degrees Celsius because the boiling point of PVA is 230 degrees Celsius. After performing this heat treatment process, we get a thin film of thickness 700 degrees Celsius. Thickness was measured by taking a cross-sectional SEM. In order to study the photoluminescence property of the films in detail, I prepared the films with different cobalt dopant concentration. The dopant concentration changes 2%, 4%, 6%, 8%, and 10%. Film with dopant concentration of 6% is taken, and it is subjected to annealing at 350 degrees Celsius, 450 degrees Celsius, 550 degrees Celsius for 1 hour. This slide will shows the XRD spectrum of cobalt-doped thin films, at different doping concentration levels. And the next slide also, this slide also shows the XRD spectrum of cobalt-doped zinc oxide films at a doping level of 6%, annealed at three different temperatures. Both the XRD spectrum shows that shows preferred orientation of zinc oxide films, that is a preferred orientation from Versat hexagonal spectrum of zinc oxide. It means that the doping or annealing does not change the host matrix, the properties of host matrix. Here I present the room temperature PR spectra of cobalt-doped zinc oxide thin films. From this graph, it is clear that the emissions peaks are centered at UV region, violet region, and blue region, and also the intensity peaks increases with the doping concentration. Next slide gives the PL spectra of cobalt-doped zinc oxide thin films at three different annealing temperatures. Here also we can observe P corresponds to ultraviolet region, violet region, and blue region. All the spectra are characterized by peaks at UV, violet, and blue region. All the emission peak intensities shows an increasing tendency with the increase in dopant level and annealing temperature. The reason for or how these violet or blue emissions are occur, that is clear from this energy level intrinsic defects of zinc oxide thin film. The visible luminescence of zinc oxide originate from different defect states such as oxygen vacancies, zinc vacancies, oxygen interstitials, zinc interstitials, and andesite oxygen. This slide gives the energy levels of intrinsic defects in zinc oxide film calculated using full potential linear muffin-tin method. From the above figure, it is clear that interface level at 3.06 electron volt, 3.06 electron volt, and 2.9 electron volt are due to the existence of zinc vacancies and zinc interstitials in the band gap of zinc oxide. Therefore, it is reasonable to conclude that violet emission from the films may be due to the radiative transition between these interface levels with conduction band or valence band of zinc oxide. The blue band emission originates from the electron transition from shallow donor level of oxygen vacancies to valence band. Oxygen vacancies can produce two defect donor levels. One is the deep donor level located at 1.3 electron volt, 1.3 electron volt to 1.6 electron volt below the conduction band, and the other one is shallow donor level below the conduction band at about 0.3 electron volt to 0.5 electron volt. The energy obtained from shallow donor level to the top of the valence band is about 2.8 electron volt, which is consistent with the photon energy of blue emission occurring from the prepared film, subjected to different doping analysis, doping temperature and doping concentration and annealing temperature. Therefore, it can be concluded that the blue emission from the obtained film can be due to the oxygen defects present in the band gap of zinc oxide host matrix. In conclusion, cobalt-doped zinc oxide thin films were synthesized by sol-gel dip coating process. Thin films were subjected to different annealing temperature and different cobalt dopant concentration. PS spectral studies were performed. All films exhibit ultraviolet, violet, and blue emission region. Thank you.
Thank you, Dr. P. Mathway. Any question from the participant side, please? One participant asking for the how do you know about the intrinsic defect in ZNO oxide?
We have a Muffington, using full potential linear Muffington method. We can have the intrinsic defect levels of zinc oxide. We can get the intrinsic defect levels of zinc oxide.
Okay, one more question from my side. As we can see the excited pattern, we have seen the big hump in the beginning itself. What is the reason behind that? Actually, we can't see the clear excited pattern. Beginning itself, we can see the hump is go on increasing.
I prepared the fillings in glass substrates. Therefore, some backscattering may occur from this glass substrates. So that may be the reason for this that type of occurring PQ.
Okay, what is the main motivation for doping the cobalt here?
Actually, I prepared a cobalt and a copper and nickel doped thin films. I prepared these films as my PhD thesis to study the most of the studies are in magneto-optical region, magnetic studies, but I take the optical studies.
Okay. One more question.
Yes, sir. There is one question from YouTube channel. Mr. Ashish Kumar is asking why carbon 60 is called as the zero-dimensional material. See, Mr. Ashish Kumar, you know, this carbon 60 is a spherical the molecule, and you know this carbon 60 molecule, its diameter, if you look at, and it is less than 100 nanometer, and that's why this carbon 60 molecule is said to be a zero-dimensional material, because all the dimensions of this carbon 60 are confined to less than 100 nanometers. So we say this as the zero-dimensional material, zero-dimensional particle, we say. I think Mr. Ashish Kumar has satisfied with this answer. And if you have still any difficulty or any questions with respect to this answer, you can post your the questions in the chat box of YouTube. Thank you. Now over to Jagdish sir. Yes, sir.
Okay, thank you, Dr. Joy. I would like to thanks to all the presenters. Now I call Dr. M. Vishwas, Department of Physics, Government Science College, Bangalore. Share your presentation and start. Dr. Vishwas?
Yeah.
Yes, sir. Please.
Sorry, is it audible?
Yes, sir. Sure.
My video is not open.
Sir, unmute my video.
It is disabled. You please check the video.
Yes, sir. Wait. You just unmute yourself, sir. In your video itself, you just unmute yourself and start presenting.
No, video is not. It is disabled. Please check the video, sir. Yeah, now it's coming. Okay. So So this is my presentation. The title of the paper is Synthesis, Characterization and Applications of Magnetic Perovskite ZnTiO3 Nanostructures. My name is Vishwas, working as a assistant professor in the Department of Physics, Government Science College, Bangalore. So first we have to know about the sol gel technique. We have used sol gel technique to prepare the ZnTiO3 thin films. So we have to convert the sol to gel form. So for that we use the precursor material, and it will be subjected to a series of hydrolysis and polycondensation processes to get the colloidal suspension, and the liquid particles will be condensed to a new phase formation that is called gel formation. So these are the two methods in sol gel technique. One is the dip coating, another is spin coating. In case of dip coating, we have to make the sol. After that, we have to use the substrates and dip that in the sol, and slowly we have to withdraw from the sol to get the thin film on the substrate surface. So here it is not uniform films. We can't get the uniform films if you use directly by hand. We have to use some motor for this method to get the uniform films. And another method is the spin coating method. This is the spin coating method. We have to place few drops of the sol on the spinner, and slowly we have to spin it, and then we can use multiple spinning process. First slow spinning, then high speed spinning, like that we can use. When it is spinned at a very high speed, say 2K RPM or 3K RPM, we get the uniform films on the substrate surface. So we have synthesized ZnTiO3 thin films by using sol gel spin coating method on silicon substrate, P100 silicon substrates. So this is the procedure to prepare the ZnTiO3 thin films. First, we have used zinc acetate dihydrate as a precursor material. It is mixed with absolute ethanol in 0.5 molar concentration, and a few drops of diethanol amine is added, and then it is acting as a stabilizer, and then solution is stirred for 3 hours to get the clear sol of ZnO. Then titanium tetraisopropoxide is mixed with absolute ethanol in the ratio 1:10, and a few drops of concentrated HCl is added as a catalyst, and then the solution is stirred for 3 hours to get a clear solution of TiO2. Then the resultant sols of ZnO and TiO2 are mixed in 1:1 ratio and stirred for 24 hours to get the ZnTiO3 sol. And then this ZnTiO3 sol is spin coated on the silicon and silicon substrates to get the ZnTiO3 thin films. So this is a film deposited on silicon substrate and annealed at 200 degrees centigrade. AFM image is like this. The ZnTiO3 is annealed at 200 degrees centigrade for 1 hour in ambient air, and you can see that the roughness is approximately 13.7 nanometer for this film. And this is the AFM image, 3D image of ZnTiO3 annealed at 300 degrees centigrade. Here the surface roughness has been changed to 19.3 nanometer. This is AFM image of ZnTiO3 annealed at 400 degrees centigrade. The roughness is 10.7 nanometer. So first we have checked the surface roughness using this AFM, atomic force microscopy. Then we have fabricated the mass capacitors using this way. First we have to use the silicon as the substrate, semiconducting material, and above which we have to coat the oxide material. Oxide means ZnTiO3 acts as a oxide surface on which you have to make metal coating as the electrodes. Means we have to make some mesh on the ZnTiO3. Using some mesh, we have to make electrodes by using aluminum evaporation. We have to make thermal evaporation of aluminum on the ZnTiO3 film, which is coated on the silicon substrate. And for backside also, we have to make a ohmic back contact by using aluminum coating to the backside also. So this acts as the MOS structure. That means top side is the metal, that is aluminum, and oxide is an insulating layer, that is ZnTiO3 is the oxide layer, and S means silicon. This is a semiconducting layer, metal oxide semiconductor capacitors. So we have used this Agilent 4155C for finding the IV characteristics and quasi-static CV measurements, and Agilent 4284 was used for high frequency CV measurements, and different masks were used for this, and dielectric constant was calculated using this relation epsilon r is equal to C into T divided by epsilon naught into A. This is for CV plots, and current density can be determined by using I by A, current divided by area. C into T means C is the oxide capacitance, T is the film thickness, epsilon naught is the relative permittivity of the medium, and A is the area of the electrodes. And resistivity is calculated using this relation V into A divided by I into T, where V is the applied voltage, A is the area of the electrode, I is the current, and T is the film thickness. So these are the equations used to find the electrical properties of the MOS capacitors. So this is the CV characteristic of the ZnTiO3 film annealed at 100, 200, 300, and 400 degree centigrade. We can see that this represents, this is the, there are three different regions in this. One is the accumulation region, depletion region, and inversion region. This is inversion region. Three regions will be there. But actually, if you consider only 100 degree annealing temperature, the quality of this MOS is not good. By seeing this diagram, we can able to see that, we can understand that this MOS structure, the CV characteristics shows that this is not in a proper structure. If you compare this with this, it looks nice. Compare it to this. So first we have annealed that at 100 degrees centigrade, and then taken the CV characteristics. Then we have annealed at 200 degrees centigrade. This is 200 degrees. Though also there is no proper accumulation, depletion, and inversion region. Next annealed at 300 degrees centigrade. This is for 300 degrees centigrade. Accumulation, depletion, and inversion region. Next annealed at 400 degrees centigrade. Here also we are getting good MOS structure like this. And we can see that if the signal frequency is increased to 10 megahertz, then what happens? This will be inverted in this way. Inversion takes place. This is actually inversion up to, see the different frequency, signal frequencies are given here. You can see that this is corresponding to 100 kilohertz. This curve is for 500 kilohertz. This is for 1 megahertz. And 10 megahertz, this is for 10 megahertz. If the 10 megahertz frequency is applied, then the reverse saturation takes place. This is the reverse saturation. Okay. And we have also done this for another annealing temperature, that is at 800 degrees centigrade. Now you see the for 800 degrees centigrade, what happened? The MOS was damaged. We can't see the inversion, depletion, or accumulation region in this. So this is not a good MOS capacitor. It won't work as a good MOS capacitor if we anneal the film at higher than 500 degrees centigrade. At 800 degrees centigrade, the MOS structure is damaged. So we are not getting the CV characteristics properly. Now this is IV characteristics. In the IV characteristics, we can see that the film is annealed at different temperatures, 200 degree, 400, and 800 degrees centigrade. And from this, we find out the leakage current. You can see the leakage current versus the gate voltage. So what we have done here is, This is for 200 degrees centigrade. Here what is happening? The current is with increasing the temperature, what is happening means this current density is reducing. This is in a reducing manner. And this is dissipation versus voltage at 400 degrees centigrade. The film is annealed at 400 degrees centigrade, and we can see that at different frequencies we can do this dissipation, means energy loss. And you can see that for 1 megahertz frequency, the noise will be more, means the dissipation will be more at 1 megahertz frequency, and 10 megahertz frequency, the maximum dissipation will be shifted to left side, means approximately at 0 voltage, there is a one single peak. And for 1 megahertz frequency, we have so many peaks, we observed so many peaks. So the dissipation will be more for 1 megahertz frequency. Same temperature, but different signal frequencies. So this is the dissipation observed at 800, annealed at 800 degrees centigrade. So the noise is more in the case of 1 megahertz frequency, and at 10 megahertz frequency, the noise is reduced, and that peak is shifted to left side, means negative bias side it has been shifted. So this is the variation in the dissipation when observed at different signal frequencies. And we calculated the dielectric constant of ZnTiO3 film annealed at 400 degrees centigrade, and it is found to be for 100 kilohertz 91.37, 500 kilohertz 55.46, 1 megahertz frequency 32.80, 10 megahertz frequency 2.89. And then we calculated current density and resistivity of ZnTiO3 film at 200, 400 and 800 degrees centigrade, and we found that it is 5.45 into 10 power minus 5 ampere per centimeter square, 2.34 in 10 power minus 5 ampere per centimeter square, 2.15 in 10 power minus 7 ampere per centimeter square, and resistivity is 1.13 into 10 power 10 ohm centimeter, 2.81 in 10 power 10 ohm centimeter, and 4.78 into 10 to the power 12 ohm centimeter. So this is the conclusion. ZnTiO3 thin films are synthesized by Sol-Gel method. MOS capacitors are fabricated on P silicon, and CV characteristics are studied at different signal frequencies and annealing temperature. Dielectric constant values of ZnTiO3 films are found to be decreased with the signal frequency, and current density values of ZnTiO3 are found to be decreased, and resistivity increased with annealing temperature. So these are some of the results observed in this study. Thank you. If you have any doubts, you can ask.
Thank you, Dr. Vishwa, sir. Any doubts from the participant side? Any questions from the participant side? Please send your question in chat box. Any questions? If there is no question, I have one question, Vishwa, sir. The leakage current is decreases in 900 degrees Celsius sample. Leakage current is decreases for increasing the temperature. Why? What is the reason behind that?
Okay, please repeat, sir.
Leakage current is decreases for 800 degrees Celsius sample. Actually, when it is heated for 800 degrees Celsius, completely drop down that leakage current. What is the reason behind that?
So this is leakage current.
Yes.
Actually, what happens is when we increase the temperature, the density of the film increases. Okay. As the density of the films increases, then the resistivity also increases. So the leakage current means it is the energy lost. So when the density is more, the energy lost will be lesser. When it is at annealed at lower temperatures, for example, the MOS capacitor also doesn't work. We have seen that here also. When you consider 200 degrees centigrade, the MOS structure is not quite good compared to annealed at higher temperatures. The regions are clear in the case of annealed at higher temperatures, whereas here the MOS is not so good in this case. Similarly, Y means the porosity will be more if the sol gel films are annealed at lesser temperatures, means at 100 degree, 200 degrees centigrade, porosity will be more, so that the leakage current will be more. If the temperature increases, porosity decreases, and the resistivity increases, and leakage current also decreases.
Okay, sir. Thank you. If there is no question, we'll move for the next session. Thanks for nice presentation, Dr. Usha, sir. Thank you.
Okay. Thank you. Thank you.
Now I call Dr. Srinivas Rao, Department of Physics, BVSR Engineering College, Andhra Pradesh. Can you please present your work?
Audible, sir. Audible, sir.
Yes, sir.
Hello, sir.
Sure.
Hello.
Yes, sir.
Sir, I am audible, sir.
Yes, sir. Yes, sir. Please go ahead.
Yes, sir. Okay, sir. Okay, okay. Sir, my visible, sir. Visible, sir. Sir, my screen is.
Sir, it is visible. Please go ahead.
Thank you for the opportunity, sir. Professor of Engineering, warm welcome and study of silicate with sir. The major lines, sir.
Hello? Srinivas Rao? Srinivas Rao? It is not clear.
Conclusion, sir.
Srinivas Rao,
Sir,
it is
sir?
not clear, sir. It is not clear. Maybe you have a network issue, I think. Can you please make sure that your connectivity is good?
On the online, sir, my signal problem is low, sir.
Srinivas Rao, can you please make sure that your connection is good? Otherwise, we'll move for another participant presentation. Okay, maybe I think Srinivas Rao is having a network issues. Now I will move for next presentations. Abhishek Palasa, JSS College, Dharwad. Mr. Abhishek, can you hear me? Abhishek? 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 Okay, we'll end this session. On my behalf and organizing committee, I would like to express my gratitude to all the paper presenters for giving excellent presentation. Thank you all. And I would like to express my sincere thanks to convener of the conference, for giving this opportunity to share the session. Thank you, one and all. Thank you.
Okay.
Abhishek, can you hear me? Abhishek? Nayak. Abhishek Kalas, can you hear me? Ishwar Nayak. Can you hear me? Unmute ಮಾಡಿ sir Abhishek. Check now. Unmute yourself, Abhishek. Abhishek, unmute yourself and start your presentation.
Sir, admin. Sir, start it.
Yeah, you please present your work.
Sir, can you hear me, sir?
Yes, sir. Sure. Start your presentation.
Sir, my topic is nano-tube polymer film for plastic solar cell. Myself, Abhishek G. Kalas. Presently, I am pursuing MSc in JSS College, Dharwad, Karnataka. And my research supervisor is Professor I.K. Naik, Assistant Professor in Physics, Government Arts and Science College, Autonomous Karwar, Karnataka. So the contents of my topic is introduction, present work, experimental, material use, sample preparation, characterization, result and conclusion, and finally the reference. So coming back to introduction, a solar cell is a specialized semiconductor device that converts visible light into electricity. So there are different types of solar cell, like inorganic solar cell and plastic solar cell. So inorganic solar cell is constructed from inorganic P and N type of semiconductors like silicon, GS, glass, etc. The third one is plastic solar cell. In this project, we have considered plastic solar cell material. So it is constructed from polymeric P and N type conducting polymers. So there are different layers of solar cell, that is single layer cell, which is the most simplest form of the cell and efficiency is very low. The second one is bilayer cell. It contains P and N junction sandwiched between two electrodes. They have low efficiency. The third one is bulk hetero cell. The active material is a blend of P type and N type conducting polymers, efficient compared to bilayer cell, that is 2.9%. So the fourth one is multi-layer cell. It contains multiple P and N junction, one over the other. The efficiency is more than bulk heterojunction cell. The fifth one is plasmoic cell. This is nanodoped cells to increase the efficiency up to 20%. So this is bilayer cell, single layer cell, and this is bilayer cell, and this is bulk hetero cell. So why do we need plastic solar cell? There are different types of like organic, inorganic, and different types of solar cell. Particularly why we have chosen plastic solar cell, that is inorganic solar cells suffer from raw material cost, infrastructure cost, and also insulation cost. In spite of enough efficiency, these many problems are there. So we have chosen the plastic solar cell. The advantage of plastic solar cell, that is it is low material cost in bulk. If bulk we are trying to do is the cost is very low. and it has good flexibility and high optical absorption, and processing also is very simple. Even a simple person can make it. So, but the drawbacks are low efficiency, low stability, and strength. Present work. So the light emitting polymer MEHPVV is used as P type of semiconductors. So here we have used two type of materials, that is P and N type of materials. That is P type of material we have used is MEHPVV, and titanium nanoparticles are used as N type of semiconductors. So the photoactive material is prepared by doping N type of titanium dioxide into P type MEHPVV at a weight ratio that is 3:1, 1:1, and 1:3. Further, when the thin film is prepared, further the samples are characterized by UV visible, fluorescence, XRD, and SEM. So the material used is P type of donor polymer, that is MEHPVV, whose molecular weight is nearly 40,000 to 70,000, HOMO 5.3 electron volt and LUMO 3 electron volt, and it is taken from Sigma Aldrich. So N type of nanoparticles, that is titanium dioxide, it is also from Sigma Aldrich. Molecular weight is 79.966 grams per mole, and the density is 4.23 cc grams per cc, and the particle size is less than 100 nanometer. So now coming back to sample preparation, the first step is preparation of P type of solution. 20 mg of MEHPVV is added to 1.125 cc of chlorobenzene, and it is magnetically stirred for 24 hours at room temperature. The step 2, that is doping with N-type titanium nanoparticles. Here the titanium nanoparticles is directly added to P type of solution. Earlier we have prepared a P type of solution. For that P type of solution, we have added titanium dioxide nanoparticles with a ratio that is P:N, with ratio 3:1, 1:1, and 1:3, and magnetically stirred about for 20 hours. We have stirred it for magnetically. So 3 samples we have prepared, that is 3:1, 1:1, and 1:3. The step 3 is preparing the glass coated samples. The doped solution is transferred to Petri plates and dried in a oven. After drying in a oven, we will get the thin film of 3:1, 1:1, and 1:3 blend. And further taking that, we have done characterization for UV visible, fluorescence, XRD, and SEM. So here is the film composition, that is P type of solution MEHPVV. We have in first sample we have used 1.5 mg, that is nearly about 9.4 cc. The titanium dioxide, that is 0.5 mg, and doping state is 3:1. In second sample we have used P type of solution, that is 1 mg, which is equal to 6.25 cc, and titanium dioxide, that is 1 mg, and the doping state is 1:1. So in third sample we have taken 0. mg of P type of solution, which is equal to 4.13 cc. So titanium dioxide we have used is 1.5 mg, and the doping state is 1:3. So coming back to the characterization, here we have prepared 3:1, 1:1, and 1:3 blend of MEHPVV is to titanium dioxide, and characterized them by JASCO UV visible NIR V670 spectrometer. The spectrum of the sample is presented as a graph of absorption A versus wavelength lambda. The film has a absorption extending from 300 nanometer to 650 nanometer, having lambda max between 520 nanometer to 550 nanometer, and with one set of absorption, that is 650 nanometer. Here we can see that absorption curve gets broadening, reduction in the band gap. The addition of titanium dioxide to MEHPVV is going to tune the absorption spectrum of MEHPVV to the maximum wavelength. So here we can see that maximum tuning has occurred in 1:3 sample. So here we can see that maximum tuning has occurred in 1:3 sample. Here the absorption spectrum is broadened, covering UV visible region and even infrared region. Comparing all the samples, among that 1:3 composite blend has the best spectral sensitivity for absorption and can be considered as a best photoactive blend for construction of solar cell. Here the Tox plot is used to determine that optical band gap or Tox gap in the semiconductor. From the Tox plot, we have calculated that energy band gap. So this is overlap of emission spectra. So in fluorescence, it's measured that the wavelength of maximum absorption of light and the intensity of the light. Here the spectrum often consists broad absorption. We can see that quenching of fluorescence. The photoactive blend with maximum fluorescence give rise to minimum charge collection, and also the peak intensity
Abhishek, can you hear me? Abhishek? Abhishek, can you hear me?
Yes, sir, I can hear, sir.
Make sure that your internet connection is good.
Sir, can you hear me, sir?
Yes.
So sometimes the polymers are not available in 100% crystalline state. They are available in amorphous state or as mixture of both amorphous and crystalline state. So they can be considered to be sometimes semi-crystalline. So by X-ray diffraction pattern, polymers consisting both sharp as well as diffuse band. So here we can see that sharp bands corresponding to the crystalline nature and diffuse band corresponds to the amorphous region. So from X-ray diffraction, we
Your
have come
screen
to
is
know
not
that
visible, Abhishek. Share your screen. Yes. Now we can start.
so there are sometimes the polymers are not available in 100% crystalline. They are amorphous. They are available in amorphous state or crystalline state. So they can be considered to be semi-crystalline. So X-ray diffraction pattern of polymers contains both sharp band as well as diffuse band. So here sharp band corresponding to the crystalline nature and diffuse band corresponding to the amorphous nature. So from XRD we can come to know that the material is amorphous in nature. So this is the SEM images of the blend. A SEM is a type of electron microscope that produces images of sample by scanning with a focused beam of electrons. Here the electrons interact with atoms in a sample, producing various signals that contains information about the sample surface, topography, and composition.
Abhishek, can you hear me? Search the ಮುಗಿಸ್ಬಿಡೋಣ. Close ಮಾಡಿ ಅವನು. Okay. Maybe there is a network problem from Abhishek. Again, you are sharing the screen. Abhishek, can you hear me? Abhishek? Abhishek?
So the result and finally the result and conclusion, we can see that the effect of titanium dioxide in the blend is to broaden and enhance the spectral absorption of MEHPBV even behind the visible region. Comparing among all the samples we have taken, we can consider that 1:3 has a wide spectrum of absorption, and it is the best photoactive blend with least band gap of 2 electron volt and maximum wavelength, that is 619.96 nanometer. So here we have taken 3:1 blend has the wavelength that is 589.62 nanometer and the energy gap is 2.10 electron volt. So in second sample 1:3, we can see that the one set wavelength is 605.32 nanometer and the energy gap is 2.04 electron volt. And sample we can see that 1:3 sample we can see that one set wavelength that is 619.96 nanometer and the energy gap is 2 electron volt. So from XRD it reveals that the material is amorphous in nature. From SEM images confirms that the formation of bulk PN junction with almost uniform distribution of Ti2. So the construction of solar cell using optimized blend is the work under the progress which we are going to do. So the finally the reference which we have used, this is all the reference which we have used it. And finally the thank you to everyone for giving me an opportunity. So it was a good opportunity for me to present the work which I have done. Thank you one and all.
Thank you, Mr. Abhishek. If there is no question,
One question from chat box. Abhishek, you are seeing the chat box. Dilip Kumar is asking that what is the full form of MEHPPV? Abhishek.
Sir, can you hear me?
Yeah, tell me.
Yeah, you are audible. Abhishek.
Repeat, sir.
What is the abbreviation of MEHPPV? Hello?
Hello, sir. Sir, polymethoxy.
Dilip Kumar is asking the question.
Sir, polymethoxy 5,2-ethyl hexyl 1,4-propylene valine, sir.
It is a polyphenylene vinylene.
Yes, sir.
If I'm not wrong, it is a polyphenylene vinylene.
Yes, sir. Yes, sir.
Okay.
Thank you, Abhishek. On my behalf and organizing committee, I would like to express my gratitude to all the paper presenters for giving excellent presentations. I would like to express my sincere thanks to organizing team for giving this opportunity to sharing the session. Thank you, Ananda. I will hand over the session to convener.
Thank you, sir. Thank you, Dr. Jagdish, sir, for chairing the oral presentation session. Now, I would like to call upon our beloved convener of this international conference, Dr. Rajesh Naik, to propose vote of thanks. Dr. Rajesh, sir.
Good afternoon to all. I, Dr. Rajesh Naik, convener of the conference and assistant professor of physics, PC Jabin Science College, Hubballi, take this opportunity to deliver a vote of thanks on the occasion of one-day online international conference on zero-dimensional materials organized by the Department of Physics. I would like to express my sincere thanks to Honorable Dr. Prabhakar B. Kore, Chairman, Board of Management, Keli Society, Belagavi, for the constant support as well. So I like to extend my sincere thanks to Board of Directors, Board of Management, life members of Keli Society, and our beloved principal, Dr. L.D. Horkere, for the unconditional support and encouragement. My special gratitude to today's invited speakers, Dr. Theodos Pavadis, Dr. S.P. Raju, and Dr. Diba Pratim Jana for spending their valuable time with us. All the sessions definitely benefited the participants who have attended. I extend my thanks to International and National Advisory Committee, Organizing Committee, and our technical team for their active involvement and successfully organizing the conference. At last, Heartfelt thank you to all the participants for their energetic and active participation. Hope you all have enjoyed the conference. Thank you, one and all. Thank you.
Thank you, sir. If anybody is interested to share the opinion orally, then you are requested to present, and please raise the hand, those who want to share the opinions. And I will meet yourself, and you can able to share your feedback about this conference. Please raise the hand. I will mute yourself, and you can share the opinion about the conference. Okay. Yes, Chandrasekhar. Yes, sir. Yes, sir. Chandrasekhar, sir.
Hello.
Yes, sir.
I would like to congratulate the entire team of KLE institution led by Rajesh Nairi and the speakers. It has been a wonderful opportunity for all the researchers and the students and the faculty members to attend the conference. We expect similar kinds of programs from the KLE institutions in the coming days. Thank you very much. On behalf of all my colleagues, I would express my sincere gratitude to the entire team. Thank you.
Yes, sir. Thank you so much, sir. Thank you so much. Yes, any other participants want to share the opinion, oral presentation, opinion? Paludi, sir.
Oh, everything was greatly organized, and I really enjoyed participating in the conference.
Yes, sir. Thank you, sir. Thank you, sir. Thank you.
Thank you for
If
inviting
any other
me.
participant want to share the opinion, oral opinions? Okay. Thank you. Now you please start the video, and so we are taking the pic of this one. So please start the video. Hello, sir.
Hello.
Yes, all of you, please. Please, all the dear participants are requested to start the video yourself. Yes, thank you so much. Thank you so much. And I thanks all the participants for attending this conference and making it grand success. And I thank our convener and our all the organizing committee members for encouraging us to organize such a conference. Thank you one and all. Now I'm sharing the feedback link of the presenter as well as participants. So please give the valuable feedback that may encourage us to conduct such a conference in future. Thank you. And I'm sharing the feedback in WhatsApp, in this WhatsApp group and this Telegram group and in YouTube as well as in the chat box. Please give the valuable feedback. Thank you one and all.
Okay, congratulations, Dr. Rajesh Nair, for successful completion of